Imagine the universe as an immense, shadowed theater, where the audience sits in darkness, unable to see the stage clearly. Occasionally, a sudden, violent explosion erupts from the wings, illuminating every seat in the hall with a blinding flash. This vivid metaphor captures our cosmic reality. We are observers seated in the dark, marveling at the dazzling lights of distant stars and galaxies, while behind the scenes, catastrophic stellar events silently unfold, performances that could at any moment bring our entire show to a permanent end. This concept is not merely poetic but deeply rooted in cosmic history. 66 million years ago, our planet experienced a catastrophe of such magnitude that it forever altered life on Earth. An asteroid, roughly the size of a mountain, plummeted from space and struck what we now know as the Yucatan Peninsula, carving out the massive Chicxulub crater. This impact was no ordinary collision. It was a cosmic reset button unleashed with an energy equivalent to 10 billion atomic bombs detonating simultaneously. Visualize a fragment between 10 and 15 kilometers wide hurtling through the void at 20 kilometers per second. An unstoppable, destructive force that, in milliseconds, excavated a crater nearly 200 kilometers across. The aftermath was apocalyptic. The impact released an unfathomable amount of energy, around 100 million megatons of TNT, making it roughly 2 million times more powerful than the largest nuclear device ever detonated by humans. Yet this explosion was merely the opening act. Within hours, a deluge of molten rock and searing debris rained down across North America, igniting wildfires and triggering tsunamis taller than skyscrapers that swept across continents. The true horror lay in what followed, a prolonged impact winter, a dark and sunless era lasting for months or even years. Imagine the sky darkening not for days or weeks but for an extended period, as a thick, choking blanket of dust and soot enveloped the entire planet, preventing sunlight from reaching the surface. Photosynthesis, life's fundamental process, ceased to occur on a global scale. Without sunlight, plant life withered and died, setting off a chain reaction of extinction. Herbivores starved without their primary food sources, and carnivores deprived of prey followed suit. The ecological dominoes fell in rapid succession, leading to the loss of approximately 75% of all species, including every non-avian dinosaur that roamed the Earth. Scientists today often cite the Chicxulub impact as their baseline example of cosmic catastrophe. Not because it was the worst possible event, but because it is the most recent example of a celestial collision we can analyze in detail. It serves as a stark reminder that such an event, or something even more devastating, could happen again. What keeps planetary defense experts awake at night isn't merely the memory of the asteroid that ended the dinosaurs' reign, but the unsettling possibility that a far larger, more destructive object might be hurtling toward us from the depths of space with little warning. And this brings us to a particularly troubling aspect of our cosmic vulnerability: long-period comets. These icy wanderers originate from the outermost reaches of our solar system in a vast spherical shell known as the Oort Cloud. These objects can appear suddenly, seemingly out of nowhere, with virtually no advance notice or warning. Their unpredictable appearances and unpredictable trajectories make them particularly dangerous in the context of planetary defense, as they could strike with catastrophic force before we even realize they are coming. While humanity has become remarkably proficient at tracking and identifying near-Earth asteroids, comets remain an entirely different challenge altogether. These icy wanderers originate from a vast spherical shell of frozen debris known as the Oort Cloud, a colossal reservoir that extends nearly halfway to the closest star. When gravitational nudges, subtle but persistent influences from passing stars or galactic tides, send one of these frigid bodies hurtling toward the inner solar system, our window for response can be surprisingly narrow, Often we have only months or perhaps a few years to detect the impending threat, analyze its precise trajectory, and if deemed necessary, strategize a potential deflection. Our recent successes in asteroid deflection give us hope. For example, NASA's DART mission in 2022 demonstrated that it is indeed possible to nudge small asteroids off their collision courses. The spacecraft successfully altered the orbit of Dimorphos, a small moon orbiting the asteroid Didymos, confirming that targeted kinetic impact can change an asteroid's path. This pioneering effort provided a vital proof of concept that such planetary defense techniques could work against certain types of threats. However, comets pose an entirely different set of challenges, making them far more difficult targets for planetary defense. One of the most significant hurdles is their speed. Comets, when they reach Earth's neighborhood, often travel faster than asteroids, sometimes at twice the velocity. This rapid pace reduces the available time to react and complicates efforts to alter their course. Additionally, comets are inherently more fragile than rocky asteroids, primarily because they are composed of loosely bound ice, dust, and rock. Their structural integrity is delicate. Applying any force or impact to deflect them risks fragmenting the body into multiple pieces, potentially creating a swarm of smaller, unpredictable projectiles rather than a single manageable threat. Furthermore, unlike many asteroids that follow predictable elliptical orbits, comets develop tails and experience non-gravitational forces as they approach the sun and heat up. The sublimation of their icy surfaces produces jets of gas and dust that can exert tiny but cumulative forces on their trajectories, making their paths more dynamic and less predictable. This tail activity and outgassing introduce uncertainties that challenge our ability to model and forecast their exact routes with precision, complicating any attempt to predict or influence their future position accurately. Despite these difficulties, modern sky surveys such as ATLAS, Pan-STARRS, and the Zwicky Transient Facility are continuously scanning the heavens each night. These automated sentinel systems have revolutionized our capacity to detect potentially hazardous objects long before they pose a direct threat to Earth. They identify more objects than ever before, significantly enhancing our planetary defense capabilities. Yet these systems are not infallible. Objects approaching from the direction of the sun, those on solar inbound trajectories, remain largely hidden until they are uncomfortably close, often too late for effective intervention. Coverage across the globe remains uneven. While improvements are ongoing, surveys in the southern hemisphere still lag behind those in the north, leaving gaps in our observational network. This disparity means some objects could approach from poorly monitored regions, increasing the risk of surprises. The distinction between asteroids and comets, though perhaps subtle to the casual observer, matters profoundly in planetary defense strategies. Asteroids are primarily composed of rock and metal, solid, predictable, and relatively straightforward to track once discovered. Comets, however, are more like cosmic snowballs, composed largely of ice, dust, and organic compounds that become increasingly active as they near the sun. The solar heat causes their icy surfaces to sublimate, creating the mesmerizing tails we admire, but also producing jets of gas that can unexpectedly alter their trajectories. Even more sobering is the realization of the scale of these objects. The Chicxulub impact, the asteroid that is believed to have caused the mass extinction of the dinosaurs, measured only about 10 to 15 kilometers across. Yet we now know that much larger comets and icy bodies exist. Over the past decade, astronomers have confirmed the existence of comet nuclei exceeding 100 kilometers in diameter. These colossal objects dwarf the dinosaur killer, making it seem insignificant by comparison. Such giants would carry enough mass and energy to cause global catastrophe on an unprecedented scale. And beyond these known giants lie the truly unknown quantities, interstellar visitors that have yet to be fully understood. The first confirmed detection of an interstellar object came in 2017, when the object known as Oumuamua streaked through the inner solar system. Its trajectory revealed it was not bound by the sun's gravity, confirming its origin from beyond our solar neighborhood. 2 years later, Comet Borisov was discovered, another interstellar wanderer. These objects serve as stark reminders that space is not empty but teeming with visitors from other star systems, more frequent than previously imagined. As our observational technology advances, allowing us to peer deeper into the cosmos with increasingly sophisticated instruments, we are beginning to comprehend the true inventory of objects that could, at least in theory, find their way to Earth. The stark truth is that if the impact event we remember, like the Chicxulub asteroid, was merely a warning, then the true catastrophic event the cosmos might unleash could be vastly more destructive than anything humanity has ever faced. What are the consequences when the universe decides to send a truly colossal object hurtling our way? This question leads us into the realm of history's most spectacular visitors, those great comets that have time and again dominated the night sky and left lasting impressions on human consciousness. These celestial wanderers aren't just passing visitors, they are the grandest of the cosmic showstoppers, burning themselves indelibly into our collective memory and serving as reminders that our solar system is home to some truly awe-inspiring and potentially dangerous spectacles. Take Hale-Bopp, the superstar of the year 1997. For a staggering 18 months, this extraordinary comet was visible to the naked eye, casting an almost surreal glow across the darkness of Earth's night sky. Its presence was not merely a fleeting glimpse, but an enduring spectacle that captivated millions worldwide. The reason Hale-Bopp was so extraordinary wasn't solely its brightness, which was remarkable enough. It was its size. The comet's nucleus, an icy core of frozen gases and dust, is estimated to have measured around 60 kilometers across, making it a genuine giant among its kind. As Hale-Bopp approached the sun, the surrounding envelope of gas and dust, known as the coma, began to swell dramatically, expanding to nearly 4 million kilometers in diameter, a size larger than the sun itself. Such an immense glow was both a scientific marvel and a cultural phenomenon. Every night, countless people ventured outside, eager to witness what many described as the most spectacular comet of their lifetimes, an awe-inspiring event that seemed almost otherworldly. Yet beneath this spectacle of wonder lay a quiet, unsettling realization. Hale-Bopp's appearance was a stark reminder that objects of colossal size, originating from the distant reaches of the solar system, can suddenly appear in our neighborhood with surprisingly little warning. The comet was first discovered only 2 years before its perihelion, the closest approach to the sun, a cosmic blink of an eye in the grand scale of celestial timescales. Such fleeting appearances are not unique in history. Humanity's past is replete with encounters with unexpected visitors. Comets that have appeared seemingly out of nowhere, often with little warning, yet leaving profound impressions. One notable example is the Great Comet of 1811, often referred to as Napoleon's Comet. It streaked across European skies for months, its enormous size and luminous tail making it impossible to ignore. Its coma, the glowing envelope of gas and dust, was larger than the sun, and its tail stretched an astonishing 60 degrees across the sky, making it one of the most impressive celestial displays ever recorded. Its appearance was so striking that superstitious observers linked it to the turbulent military campaigns of the time, foretelling upheaval and change, including the eventual downfall of Napoleon in Russia. While modern science understands better than to attribute earthly events to celestial visitors, the timing of such comets often seem to carry ominous significance to those witnessing them. fueling fears and superstitions. What fascinates and unnerves astronomers alike are the characteristics these great comets often display. They are prone to dramatic outbursts, sudden, unpredictable intensifications of brightness caused by the comet's nucleus ejecting vast amounts of material in a short burst. These outbursts can cause the comet's brightness to increase by factors of hundreds or even thousands within a matter of hours or days, rendering them even more spectacular and more unpredictable. Despite decades of study, these phenomena remain poorly understood, serving as stark reminders of how little we truly grasp about these icy relics from the early days of our solar system, wandering through space with secrets yet to be uncovered. An additional feature that has long captivated both scientists and the public is the eerie green glow many comets display, especially those that have appeared in recent times. This luminous hue has sparked a host of conspiracy theories and alien speculations. However, the reality behind this ghostly light is rooted in simple chemistry. It arises from molecules such as diatomic carbon and cyanogen fluorescing when energized by solar radiation. Natural processes occurring as sunlight interacts with the molecules in the comet's coma. It's neither alien technology nor toxic gas, but rather a beautiful demonstration of the fundamental chemistry of space, a spectral signature of the universe's building blocks illuminated by the sun's energy. The same fundamental element, carbon, that forms the very backbone of all life on Earth continues to surprise and humble astronomers with its silent yet profound presence in the vast emptiness of space. This simple yet vital molecule glows faintly in the vacuum of the cosmos, a quiet reminder that the building blocks of life are scattered far beyond our planet. Despite the remarkable advancements in our observational technology, the appearance of enormous comets still catches us off guard, revealing just how much remains unknown about the far reaches of our solar system. In the days before our current era of automated sky surveys, most comet discoveries were made by dedicated amateurs or accidental sightings, people with a passion for the night sky who happened to stumble upon these celestial visitors. Their discoveries, often remarkable in their own right, were rare gems in a time when our tools for celestial detection were limited and primitive. Today, even with state-of-the-art detection networks that scan the skies relentlessly, we are occasionally blindsided by comets seemingly appearing from nowhere, already bright enough to be seen with the naked eye, bright messengers from the dark, distant fringes of our cosmic neighborhood. The geometry of each comet's encounter with the sun plays a vital role in shaping both its spectacular visual spectacle and its potential threat to Earth. A comet's closest approach to the sun, known as perihelion, governs how much solar energy it absorbs. The closer a comet comes, the more solar heating it experiences, which causes its icy surface to vaporize and release gases in a process called outgassing. This activity forms the luminous tails that captivate astronomers and stargazers alike, vast streams of gas and dust stretching millions of kilometers across the sky. But this same process makes the comet's path more unpredictable, as the forces exerted by outgassing can nudge it off course in ways that are difficult to forecast accurately. Some comets, such as Atlas C divided by 3IATLAS L3, are so heavily affected by thermal stress that they literally disintegrate as they swing close to the sun, breaking apart into multiple fragments. These fragments can continue on their chaotic journeys, creating even more spectacular and unpredictable displays. From a planetary defense perspective, these historical grand visitors serve as stark reminders that large, active objects regularly venture into the inner solar system. Although their dazzling tails and brilliant appearances might evoke a sense of menace, it is crucial to distinguish between visibility and danger. Brightness alone does not dictate threat level. A small comet passing at a close distance might shine brilliantly, yet pose less risk than a larger, darker object passing farther away. Throughout human history, comets have often been seen as harbingers of doom, woven into the mythologies and superstitions of cultures worldwide. Ancient Chinese astronomers meticulously documented the appearance of comets, interpreting them as divine omens signaling impending dynastic upheavals or natural calamities. In medieval Europe, comets were viewed as celestial signs of divine displeasure, portents foretelling plagues, wars, or famines. While scientific understanding has long since replaced superstition, there remains a primal, almost visceral fear these wandering visitors evoke. It may stem from an evolutionary memory of genuine cosmic threats, reminders of cosmic bodies that have, in the distant past, caused catastrophic events on Earth. This anthropological connection between comets and catastrophe is not entirely unfounded. Though most comets pose no direct threat to our planet, they act as living symbols that space is not an empty void, but a dynamic environment where objects from the farthest reaches of the solar system can and do venture inward. Each great comet we observe provides a preview, a fleeting glimpse into the distant reservoir known as the Oort Cloud, a vast, icy storage space that holds countless potential visitors. We are only beginning to comprehend the true scale and diversity of this cosmic reservoir. Some of these visitors are not even native to our solar system, but are interstellar travelers, passing through our neighborhood for a brief, unpredictable visit. And if the surprise element makes these comets so unnerving, what should we think about visitors that are not even bound by our sun's gravity? Part 3. The alien visitor 3IATLAS introduces a phenomenon of unprecedented significance for 2025, confirmation of the third interstellar object to traverse our solar system. This alien visitor, unlike any comet or asteroid previously observed, signals a new chapter in our understanding of the cosmos, emphasizing that our celestial neighborhood is more interconnected and dynamic than we have ever imagined. Designated as 3IATLAS, or more formally known as C2025N1, this cosmic nomad has established itself as only the third confirmed visitor from beyond our solar system. Its arrival follows the enigmatic interstellar object Oumuamua in 2017 and the spectacular comet Borisov in 2019. What truly defines an object as interstellar isn't merely its origin, where it came from, but rather where it's headed. Unlike comets and asteroids born within our solar domain, which trace elliptical sun-bound orbits, interstellar objects race through space on hyperbolic trajectories. In straightforward terms, they are traveling so swiftly that although the sun's gravity can bend their paths, it cannot capture them into orbit. They make a single pass through our system, swing by once, and then continue their journey into the vastness of interstellar space, never to return. The media has seized upon 3IATLAS's glowing greenish appearance, often breathlessly speculating about alien technology or extraterrestrial craft. Yet the scientific reality paints a far more mundane and equally fascinating picture. That haunting green hue is almost certainly caused by the same phenomena observed in ordinary comets. It results from fluorescence, emission of light, from diatomic carbon molecules and cyanogen energized by the sun's radiation. This is not evidence of alien engineering or mysterious probes. Rather, it underscores that interstellar space contains the very same basic chemical building blocks found throughout our solar system. On October the 29th, 2025, 3IATLAS reached perihelion, the closest approach to the Sun, at a distance of roughly 2.5 astronomical units, placing it beyond the orbit of Mars. This timing was a precious window for astronomers, providing an ideal opportunity to observe an interstellar visitor during its most active phase. As solar heating intensified, the object would outgaze more vigorously, shedding material and revealing vital clues about its composition and structure. For scientists, 3IATLAS is essentially a natural laboratory, a rare chance to compare an object formed around a star in another part of the galaxy with the comets native to our own solar neighborhood. The questions they are asking are profound and far-reaching. Do interstellar comets harbor the same mix of ices and organic compounds as those we find locally? How do the different stellar nurseries across the galaxy influence the chemical makeup of such objects? And what can this visitor reveal about the conditions under which it formed, possibly billions of years ago, and the environment of its origin? The discovery of 3IATLAS follows a pattern that has become all too familiar. It was first spotted by automated survey systems like ATLAS, the Asteroid Terrestrial Impact Last Alert System, which initially flagged what appeared to be a routine comet or asteroid. However, follow-up observations quickly uncovered something extraordinary. Its trajectory was hyperbolic, indicating it was hurtling through our solar system at a velocity too great for gravitational binding. Multiple observations over several weeks were necessary to confirm its path and eliminate measurement errors, tracking its precise course through space. The unsettling thought that should keep us awake at night is this: if we have already identified 3 interstellar objects passing through our neighborhood in less than a decade, then how many faint, smaller, or less conspicuous ones have slipped by unnoticed? The universe is teeming with such visitors, and many may remain hidden, undetectable with current technology. The implications are profound, suggesting that our cosmic environment is far more dynamically populated with interstellar travelers than we have yet realized. Our current methods of detection are inherently biased toward identifying objects that are either large in size, highly reflective, or actively emitting gases, phenomena that make them stand out against the darkness of space. This means that a dark, inert interstellar asteroid, particularly one approaching from the direction of the Sun, could easily slip past our surveillance systems entirely, remaining unnoticed until it is dangerously close. The rapid velocities at which interstellar objects travel introduce a set of unique and formidable challenges for planetary defense. For example, the recent discovery of the interstellar visitor designated 3IATLAS, like its predecessors, is hurtling through space at approximately 30 kilometers per second relative to the Sun. This speed is significantly faster than the typical velocities of objects native to our solar system. At such velocities, even if we manage to detect a potentially hazardous interstellar object years in advance, attempting to alter its course would demand a set of deflection techniques that are fundamentally different from those currently being developed for more familiar asteroids and comets. These conventional methods rely on gradually nudging objects with kinetic impactors or using gravitational tractors, strategies that may be ineffective against objects moving at such blistering speeds. Now let's confront the elephant in the room: the persistent and often controversial speculation surrounding the possibility of extraterrestrial technology influencing these objects. Major space agencies like NASA and the European Space Agency maintain that all 3 confirmed interstellar visitors, Oumuamua, Borisov, and 3IATLAS, are consistent with natural phenomena observed elsewhere in the universe. Yet, despite this stance, these agencies are studying each visitor with an unprecedented level of detail and intensity, driven by the potential significance of these objects. The scientific method compels us to examine every plausible explanation, including the most exotic ones, with a cautious and skeptical eye. The controversy surrounding Oumuamua exemplifies this delicate balance. When this object exhibited slight deviations from purely gravitational motion, speeding up in ways that could not be fully explained by gravity alone, some researchers proposed outlandish hypotheses, suggesting it could be an artificial construct such as a light sail or even an alien probe. However, the mainstream scientific consensus has gradually converged on more conventional explanations. These include outgassing of hydrogen or sublimating organic compounds which can produce tiny but detectable thrusts, or the influence of solar radiation pressure on an object with an unusually irregular shape. In contrast, Comet Borisov behaved exactly like a typical comet, complete with a visible coma and tail. Spectroscopic analysis of Borisov's composition revealed it to be closely aligned with comets originating from our own Oort Cloud, implying that the fundamental processes involved in planetary formation and cometary composition are likely universal features of stellar systems throughout the galaxy. What makes 3IATLAS particularly intriguing is its apparent display of typical cometary activity, such as outgassing and tail formation, while simultaneously being an interstellar object from beyond our solar system. This duality offers astronomers the extraordinary opportunity to study an alien object that exhibits familiar behaviors, thus allowing for direct comparison with the native population of our solar system's comets. The implications of this are profound, extending beyond pure scientific curiosity. These interstellar visitors act as natural test beds for our detection and response capabilities, systems that we are actively developing to defend Earth against more conventional threats. Each hyperbolic orbit we track, each measurement of composition, and every behavioral anomaly we catalog are enhancing our ability to discern between natural phenomena and potentially artificial objects. The uncomfortable truth is that if interstellar visitors are frequent enough to be detected 3 times within less than a decade, then they are likely far more common than we previously believed. This suggests a universe teeming with such objects, many of which could remain undetected due to their small size, lack of activity, or stealthy trajectories. The possibility that we are only beginning to glimpse this hidden population raises profound questions about our understanding of the cosmos and our place within it. Most of these cosmic visitors are probably too diminutive, cloaked in darkness, or inactive to be detected with the tools currently at our disposal. Yet, as our survey capabilities advance, thanks to more sensitive instruments, broader sky coverage, and more sophisticated detection algorithms, we can anticipate uncovering a growing number of these celestial nomads traversing our immediate cosmic neighborhood. And if the regular passage of alien snowballs, small icy bodies from distant star systems, is indeed a common phenomenon, then one must wonder, what about the existence of colossal alien ice mountains? What colossal yet unseen structures might be lurking in the depths of interstellar space, hidden from our view because we lack the means to perceive them? Could there be enormous icy formations drifting silently, waiting to be discovered? This brings us to part 4 of our cosmic exploration, the monster approaching, and it centers on a truly extraordinary object, Bernardinelli Bernstein, designated as 2IATLAS UN 271. In the grand catalog of cosmic nightmares, those rare, awe-inspiring objects that evoke both fascination and dread, few evoke the same potent mixture of curiosity and fear as this one. It is a behemoth of icy debris, a celestial giant that has captured the imagination of astronomers and the public alike. Discovered only in 2021 after meticulous analysis of data collected by the Dark Energy Survey, an ambitious project primarily designed to map the large-scale structure of the universe, this object has earned a remarkable distinction. It is the largest comet nucleus ever measured. Imagine, if you will, a colossal mountain range floating serenely through the emptiness of space. Most comet nuclei are modest, just a few kilometers in diameter. A collection of dirty, icy snowballs that could comfortably fit within a major metropolitan area. But Bernardinelli Bernstein is a different kind of giant. Spanning approximately 137 kilometers across, it surpasses the size of Rhode Island, turning it into a true planetary-scale interloper. Its volume is roughly 1,000,000 times greater than that of a typical comet, containing enough ice and rock to fill a significant portion of Earth's oceans, if, of course, all that ice were to melt. The story of its discovery reads like a detective novel. Two astronomers, Pedro Bernardinelli and Gary Bernstein, were sifting through years' worth of archived images from the Dark Energy Survey, a project primarily aimed at understanding the universe's grand architecture. Hidden within those images recorded between 2013 and 2019 was something unexpected. A faint, slow-moving object dwelling in the distant outskirts of our solar system. Further observations confirmed what the data implied. This was no ordinary trans-Neptunian object. It was a celestial giant of unprecedented proportions, a true monster of ice and rock. Looking ahead, this enormous object is scheduled to make its closest approach, its perihelion, in the year 2031. Even then, it will remain well beyond the orbit of Saturn, approaching within approximately 10.9 astronomical units of the Sun. To put that into perspective, this distance is still comfortably beyond Earth's orbit, and it poses no immediate threat to our planet. Yet what makes this so unsettling is not its current trajectory or safety. It's what it represents. A terrifying glimpse into the hidden icy realms lurking at the fringes of our solar system. Realms that could harbor objects of unimaginable size and mass. Astronomers have used the Hubble Space Telescope and other advanced instruments to verify the enormity of Bernardinelli-Bernstein through detailed thermal modeling. As it gradually inches closer to the Sun, solar heating begins to cause its surface ice to sublimate, transform directly from solid to vapor, creating a faint, measurable coma around the nucleus. By analyzing the brightness and thermal emissions of both the nucleus and its surrounding envelope, scientists have determined that this solid core alone measures approximately 137 kilometers across. This makes it not only the largest comet ever observed, but potentially the largest object in the entire Oort Cloud, the vast, distant reservoir of icy bodies that surrounds our solar system. Now here's where the mathematics becomes downright sobering. Let's imagine a hypothetical scenario. What would happen if an object of this magnitude were to collide with Earth? To be absolutely clear, this particular comet, as magnificent as it is, poses no threat of impact. But in the realm of theoretical risk analysis, contemplating such an event reveals the scale of potential devastation. The consequences would be truly beyond anything we could easily comprehend. The sheer energy released by such an impact would dwarf the asteroid that ended the reign of the dinosaurs, a catastrophe of planetary proportions. It's a reminder that objects of this size, lurking silently in the far reaches of our solar system, could pose an existential threat if their trajectories were to unexpectedly shift, or if they were to be perturbed into a collision course. While there is no current indication that Bernardinelli-Bernstein is headed toward Earth, the implications of its existence extend far beyond that. A celestial body measuring approximately 137 kilometers across, hurtling through space at velocities typical of comets, would possess an astonishing amount of kinetic energy, roughly 1,000 times greater than the impactor known as Chicxulub, which ultimately brought the reign of the dinosaurs to an abrupt end. Such an impact would be nothing short of catastrophic, capable of carving out a crater several hundred kilometers in diameter. Instantly, it would vaporize everything within thousands of kilometers of the impact site, unleashing destruction on a planetary scale. The shockwave traveling through the atmosphere would trigger a cascade of global earthquakes and volcanic eruptions, while impacts into the oceans would generate tsunamis so vast that they could scour entire continents clean of life and infrastructure. The long-term climate repercussions would be severe, making the aftermath of the Chicxulub impact seem mild by comparison, potentially plunging the Earth into a prolonged planet-wide winter. But before succumbing entirely to such a nightmarish scenario, it's crucial to step back and examine what the discovery of Bernardinelli Bernstein truly reveals about our cosmic neighborhood. Its existence serves as irrefutable evidence that immense ancient giants inhabit the Oort Cloud, the vast spherical shell of icy debris that encircles our solar system. This remote reservoir stretches roughly halfway to the nearest star, Alpha Centauri, and contains the primordial remnants of our solar system's formation some 4.5 billion years ago. Most of its contents remain locked in deep freeze, rendering them invisible to our current telescopic eyes. Nonetheless, gravitational nudges, subtle pulls from passing stars or galactic tides, occasionally disturb these icy bodies, sending them tumbling inward toward the inner solar system. The discovery of Bernardinelli Bernstein indicates that our understanding of the true population within the Oort Cloud has been incomplete. If such a colossal object can exist, discovered only because it fortuitously passed through the narrow observational window of a dedicated survey, then countless others, perhaps even larger or more dangerous, could still be lurking in the darkness beyond our direct view. From a planetary defense perspective, objects of this magnitude pose extraordinary challenges. Their immense size and mass render current and foreseeable deflection technologies nearly ineffective. For instance, methods like NASA's DART mission, which successfully nudged a small asteroid off course, would be utterly powerless against a behemoth like Bernstein. Attempting to fragment such a space giant with nuclear devices might create a debris field so widespread that it would itself become an even more significant threat to Earth. The most pragmatic approach, therefore, hinges on early detection and, if necessary, evacuation, assuming we have decades or even centuries of warning. Fortunately, the orbital mechanics of long-period comets work in our favor. These objects take millions of years to complete their journeys from the distant Oort Cloud into the inner solar system. Unlike potentially hazardous asteroids, which may be spotted only months or a few years before a close approach, true long-period comets can be identified decades in advance, providing valuable lead time for preparation. This is where upcoming technological advancements like the Vera Rubin Observatory come into play. Set to revolutionize our ability to monitor the cosmos, this facility will conduct a comprehensive survey of the entire visible sky every 3 nights. Its advanced imaging capabilities will allow it to detect moving objects with unprecedented efficiency and accuracy, far surpassing current systems. Computer models predict that the Vera Rubin Observatory could increase our discovery rate of long-period comets by an order of magnitude or more, ultimately enabling astronomers to compile the most comprehensive inventory yet of the icy denizens lurking in the outer reaches of our solar system. This enhanced awareness is vital for planetary defense, as it transforms what was once an unpredictable threat into a manageable risk, at least in principle, by providing ample warning to develop potential response strategies well in advance of any approach. The media portrayal of Bernardinelli Bernstein vividly illustrates the dual-edged nature of science communication in our digital era. Headlines tend to spotlight the sheer magnitude of this colossal comet, emphasizing its extraordinary size, yet often omit the crucial detail that it poses no imminent threat to Earth. This imbalance presents a delicate challenge for scientists and communicators alike. How can they convey the profound scientific importance of such discoveries without inciting undue public fear? The solution, as many experts agree, rests in providing proper context and fostering education. Bernardinelli Bernstein stands out precisely because it is so uncommon. Its immense size transforms it into a natural laboratory for examining the pristine materials from our solar system's infancy, offering insights into its original composition and structure. Its well-defined, predictable trajectory grants astronomers years of advance notice, allowing for meticulous planning of observations and research. Additionally, its considerable distance from Earth ensures that we can study it safely, without any risk of collision or harm. Nonetheless, beneath these reassuring facts lies an unsettling possibility. If a comet of sto-tritsit kilometers in diameter can exist, what is the upper limit? How enormous might these cosmic monsters become? Let us venture into the realm of pure speculation, a mental exercise that often keeps planetary defense specialists awake at 3 in the morning. Imagine for a moment two hypothetical comets, one named Thanatos, measuring 300 kilometers across, and the other called Leviathan, a staggering 500 kilometers in diameter. Objects that dwarf even Bernardinelli Bernstein. It is important to clarify that these are thought experiments, not real celestial bodies, but they serve to illustrate the kinds of cosmic nightmares that could, in theory, lurk in the distant outskirts of our solar system. Thanatos, the smaller of the two, would contain roughly 27 times the mass of Bernardinelli Bernstein. If such an object were to collide with Earth, remember, we are still firmly in the speculative domain. The consequences would be catastrophic beyond anything documented in Earth's geological history. The impact energy would be equivalent to approximately 100 million megatons of TNT, resulting in the formation of a crater exceeding 1,000 kilometers in diameter. Such an event would unleash seismic shocks powerful enough to register magnitude 10 or higher on the Richter scale. Earthquakes so intense that they could crack the very crust of the planet itself and induce global tectonic upheavals. Taking this to the next level, Leviathan, the hypothetical 500-kilometer comet, would dwarf Thanatos in scale and destructive potential. An impact from such a behemoth would release energy comparable to the forces that formed Earth's very moon, an event believed to occur only once in the entire history of our solar system. This collision could potentially strip away Earth's atmosphere entirely and cause the oceans to boil away into space, effectively sterilizing the planet and rendering it uninhabitable for millions of years. A crucial point that often gets lost amid sensationalist discussions about cosmic catastrophes is the distinction between size and orbital mechanics. Size alone does not determine whether an object will threaten Earth's orbit. Even a comet measuring 500 kilometers across would not gravitationally destabilize our planet, unless it were to pass within a few Earth radii, an extremely close approach by cosmic standards. The real danger posed by these colossal objects is not their gravitational influence, but the immense energy they release upon impact. When such a colossal comet strikes, the physics of deflecting it with current planetary defense strategies becomes practically irrelevant. Present methods, like nudging small asteroids over years or decades, are designed to mitigate relatively minor threats. They rely on delivering modest amounts of energy to subtly alter an object's trajectory, buying time and reducing risk. However, at scales of hundreds of kilometers, the kinetic energy involved is so vast that even the most advanced technology would be powerless to prevent catastrophe. In these scenarios, physical destruction through impact becomes inevitable, and the physics of impact energy release dominates. The demonstration of NASA's dark mission principle underscores a stark reality. While our current planetary defense strategies are effective against smaller objects, they are utterly inadequate when it comes to colossal cosmic threats. Kinetic impactors, the primary tools we have for nudging or redirecting smaller asteroids, would be completely ineffective against objects of such enormous scale. Similarly, even nuclear devices, often considered as a last-ditch effort to alter an impending impact, would be like trying to halt a freight train with a single firecracker. The sheer energy involved in these massive objects renders conventional deflection methods hopelessly insufficient, which is where the volatile nature of comets becomes both a surprising asset and a significant liability. Unlike solid metallic asteroids, comets are essentially fragile conglomerates of ice, rock, and organic molecules loosely held together. This delicate composition means that the same thermal stresses and outgassing phenomena that create their spectacular tails and luminous displays can also make them prone to fragment into countless smaller pieces. In theory, a precisely calibrated nuclear explosion might shatter a large comet into smaller fragments, but this approach introduces a new set of dangers. The resulting debris cloud could be even more perilous than the original object, scattering dangerous fragments across a broader area and increasing the likelihood of multiple impacts rather than preventing a single catastrophe. Our ability to detect these gigantic objects well in advance is both a saving grace and a source of potential chaos. If an object of such magnitude were on a collision course with Earth, it would likely be visible through our current survey systems decades before it reached the inner solar system, assuming it approached from a favorable direction and was bright enough to be detected. However, confirming its exact trajectory and assessing the threat level would take months or even years of meticulous observation and analysis. During this uncertain period, public reaction could spiral into panic, potentially causing social and economic disruption equal to or greater than the threat posed by the object itself. This looming uncertainty is compounded by significant gaps in our detection capabilities. Most of our asteroid and comet monitoring systems are concentrated in the northern hemisphere, leaving vast regions, particularly in the southern hemisphere, less well covered. As a result, objects approaching from the sun's direction remain largely hidden until they are uncomfortably close, giving us very little time to respond. Additionally, comets arriving from high-inclination orbits, those passing above or below the plane of the solar system, may evade detection until their approach is nearly imminent, further reducing our reaction window. Fortunately, the upcoming Vera Rubin Observatory promises to revolutionize our planetary defense efforts. With the capability to scan the entire visible sky every few nights, it will vastly increase our ability to detect and catalog moving objects with unprecedented efficiency. Computer simulations project that this facility could identify hundreds of thousands of new asteroids and comets, providing us with a detailed and comprehensive census of potentially hazardous objects lurking in our cosmic neighborhood. Such an extensive inventory would dramatically improve our understanding of the risks, allowing for better predictions and preparedness. Nevertheless, even the most advanced surveys cannot eliminate every blind spot. Comets are notorious for experiencing dramatic changes in brightness due to outgassing and fragmentation, phenomena that can occur suddenly and unpredictably. A comet that appears small, harmless, or even dormant might unexpectedly flare to many times its original brightness, revealing a much larger nucleus or a dangerous fragmentation event. Conversely, a large comet could remain deceptively faint if its surface becomes coated with non-volatile materials that suppress outgassing, making it less conspicuous than it truly is. The temporal aspects of such mega-impacts introduce a complex paradox. On one hand, decades of warning might allow us to prepare, evacuate, or attempt deflection. On the other hand, the psychological toll on the public could be devastating. Learning with mathematical certainty that a civilization-ending object is on a collision course could induce widespread panic, economic instability, and political upheaval. How would governments respond? Would nations cooperate on a global scale, or would fear lead to isolationist and catastrophic decisions? Would humanity rally behind efforts to mitigate the threat, or would fear and misinformation drive us into chaos? These questions highlight the immense challenge of managing knowledge of such a colossal danger. A danger that could strike suddenly or be known for decades only to be impossible to stop once the impactor is too close. The stark reality is that despite rapid advancements in our planetary defense systems, our current capabilities are still glaringly inadequate when faced with truly colossal cosmic threats. We are honing techniques that might prove effective against objects roughly tens to hundreds of meters in size, those city-killer asteroids that can wreak havoc on a regional scale. Our successes, such as demonstrating the ability to nudge small asteroids like Dimorphos off their trajectories, provide a glimmer of hope, yet they fall far short of confronting the larger, more destructive bodies that lurk in the dark expanses of space. Against hypothetical behemoths like Thanatos or Leviathan, asteroids or comets measuring hundreds of kilometers across, our most reliable strategy would hinge on the earliest possible detection, followed by what? Extensive mass evacuation efforts. The construction of underground shelters to safeguard the vulnerable. Long-term survival plans that might sustain humanity through a cosmic catastrophe. These scenarios force us to confront the stark limits of human technological prowess. We are quite literally only a single cosmic accident away from potential extinction. The only solace, albeit a cold one, is rooted in the mathematical improbability of such devastating events occurring within the span of human existence. The larger the impactor, the more astronomically rare its occurrence. Yet history and the universe itself have already demonstrated an uncanny capacity for delivering shocking surprises. Who could have predicted the existence of interstellar visitors such as Oumuamua? Who foresaw the discovery of a comet as gargantuan as Bernardinelli Bernstein, measuring approximately 137 kilometers across? As our observational tools become more sensitive, our surveys more comprehensive, we are increasingly revealing that our solar system harbors far more large objects than previous models suggested. If ice mountains like Bernardinelli Bernstein represent the extreme end of solar system threats, what other cosmic predators might be lurking unseen in the shadows of the universe? Could there be entities that dwarf even 500-kilometer comets, entities that make these icy behemoths seem like harmless specks of cosmic dust? Let's delve into the realm of the unseen. Part 6. The Invisible Killers. Among these, rogue black holes stand out as some of the most terrifying. Hidden in the vast darkness between stars, these invisible predators drift through our galaxy like cosmic sharks, silently hunting. Stellar mass black holes ejected from their original birthplaces in violent supernova explosions now wander freely through interstellar space, unseen and undetectable unless they pass close enough to produce observable effects. Until recently, the existence of these rogue black holes was confined mostly to the realm of theoretical models and computer simulations. It was only in 2022 that the Hubble Space Telescope provided us with our first confirmed glimpse of one such elusive entity. This breakthrough came through a process known as gravitational microlensing, an effect predicted by Einstein but never before directly observed in such detail. When a massive object like a black hole passes between Earth and a distant star, its gravity acts as a gravitational lens, temporarily magnifying the star's light. Over a span of 6 years, Hubble meticulously tracked one such event, observing how the gravity of an unseen object distorted the light emanating from a star approximately 25,000 light-years away. The detailed analysis revealed something extraordinary. A black hole roughly 7 times the mass of our Sun, drifting silently through the galaxy at a speed of about 45 kilometers per second. This discovery was not merely an academic curiosity. It was a tangible proof that our worst cosmic fears might be justified. It confirmed that these invisible killers are not just figments of theory, but real entities lurking in the darkness. Astronomers now estimate that our galaxy contains around 100 million stellar mass black holes, most of them entirely hidden from view, detectable only when they happen to pass in front of a distant star or other luminous source. These dark denizens of the galaxy drift silently, their presence revealed only through their gravitational influence, a silent testament to the universe's capacity for both wonder and terror. The universe is teeming with unseen cosmic predators lurking in the shadows, their paths weaving through space along trajectories that we cannot reliably predict. These invisible travelers, rogue black holes, possess enough gravitational pull to unsettle entire planetary systems should they venture too close. But what truly constitutes too close when talking about such formidable objects? The mathematics surrounding this question oscillates between reassurance and dread, revealing both our fragile safety and the terrifying potential for catastrophe. A black hole with a mass comparable to a typical star, what scientists call a stellar mass black hole, would need to pass within approximately 1,000 astronomical units of our solar system to cause significant disturbance. To put that into perspective, it's roughly 25 times the distance from Earth to Pluto. At such a proximity, the black hole's immense tidal forces would begin to stretch and squeeze Earth's crust, setting off a chain of geological upheavals, massive earthquakes and volcanic eruptions that could profoundly reshape our planet long before the black hole actually captures Earth or flings us outward into the cold depths of interstellar space. The likelihood of such a close encounter, while unsettling to consider, is actually remarkably small, comparable to winning the lottery multiple times in succession. This statistical rarity offers a measure of comfort, yet the consequences of even a single such event would be catastrophic beyond imagining. Unlike asteroid impacts, which might obliterate human civilization but leave Earth's fundamental structure intact, a close pass by a rogue black hole would fundamentally alter Earth's position within the solar system. Such an event could render the planet uninhabitable for billions of years, wiping out life as we know it. Our understanding of these dark wanderers has been revolutionized by the recent discovery of a confirmed rogue black hole, an object that has profoundly reshaped our view of galactic populations. Computer simulations suggest that these black holes are born during the violent deaths of massive stars, explosive supernovae. When such an explosion is asymmetric, ejecting more material in one direction than another, it imparts a powerful natal kick to the newborn black hole. This kick can accelerate the black hole to velocities of hundreds of kilometers per second, fast enough to escape the gravitational grip of its parent star system entirely. Some of these escaped black holes have been wandering the galaxy for billions of years, cloaked in invisibility, their presence known only through their gravitational influence. They are cosmic hitchhikers carried along by the rotation of the Milky Way, not bound to any particular star, and representing remnants of the galaxy's violent youth. These ancient black holes are like fossils, silent witnesses to the primordial processes that shaped our galaxy long before our solar system was even a concept. Detecting these elusive objects is a formidable challenge. Black holes do not emit light. Instead, they are nature's perfect absorbers of radiation. The only way to detect isolated black holes is through indirect methods, gravitational effects that betray their presence. One such method is microlensing, where the black hole's gravitational field briefly magnifies the light from a background star as it passes in front. The Hubble Space Telescope has already observed such microlensing events, offering tantalizing glimpses into the population of rogue black holes. Additionally, the gravitational waves produced when black holes collide with other massive objects provide another detection avenue. The upcoming Nancy Grace Roman Space Telescope promises to dramatically enhance our ability to identify these dark objects. Its advanced microlensing survey capabilities could reveal thousands of additional rogue black holes lurking within our galactic neighborhood, hidden from view until their gravitational influence makes itself known. But even as we make strides in detection, the story takes an increasingly unsettling turn. The black hole Hubble first detected was not the largest or most perilous of its kind. It was simply the first one we observed lensing a background star, an accidental glimpse into a vast, unseen population. Recent discoveries suggest that the number of such massive remnants wandering through our galaxy might be much greater and more diverse than previously believed. For example, in 3IATLAS analysis of data from the European Space Agency's Gaia mission revealed the existence of BH3, a black hole with a mass of approximately 33 times that of our Sun, located just 3 light-years from Earth. This revelation underscores how many of these cosmic nomads are out there, quietly drifting through the galaxy, their presence known only through their gravitational signatures. The sheer abundance of these stellar remnants raises profound questions. How many more are hidden in the dark? Could some of these black holes, traveling at hundreds of kilometers per second, someday pass close enough to our solar system to cause a planetary upheaval? The potential risks are real, and the challenge of detecting these invisible giants is immense. Nestled just 2,000 light-years away from our planet lies a colossal stellar mass black hole, an entity whose weight tips the scales at approximately 33 times the mass of our Sun. This remarkable object holds the distinction of being the most massive black hole of its kind ever discovered within our entire galaxy. Unlike the solitary rogue black hole detected in the past by the Hubble Space Telescope, this one, designated BH3, was identified thanks to its dance with a companion star. It was the gravitational influence of this neighboring star that allowed astronomers to detect its presence, highlighting how critical such partnerships are in unveiling these cosmic giants. Yet the sheer size of BH3 raises profound and unsettling questions about how many other such giants might be quietly drifting through the vast, dark expanses of interstellar space. Completely hidden from our view, the physics governing encounters with these behemoths become increasingly surreal as their proximity shrinks. At a distance of only a few dozen astronomical units, roughly the scale of our outer solar system, the implications grow ever more terrifying. A rogue black hole approaching this close would not merely disrupt planetary orbits, it would begin to rip apart the outer planets themselves via intense tidal forces. Imagine the outer planets, Jupiter's moons, being scattered like billiard balls across the void, their orbits shattered by gravitational shear. Saturn's majestic rings, once a stable, shimmering band, would be twisted and contorted into spiraling chaos before ultimately being consumed entirely by the black hole's insatiable appetite. What's even more disturbing is the stark realization that such an intruder might arrive undetected, slipping through the cosmic shadows without warning. Unlike comets, which grow brighter and more visible as they approach the Sun, black holes remain invisibly silent until their gravitational influence becomes unmistakably evident. By the time we observe the orbital disturbances in our outer planets, the rogue black hole could be perilously close, so near that any attempt at evacuation or deflection would be hopelessly unfeasible. The upcoming space telescope, known as the Roman Space Telescope and scheduled for launch in the mid-2020s, offers our most promising hope of cataloging these invisible threats. Equipped with a wide-field infrared camera, it will monitor hundreds of millions of stars simultaneously, vigilantly searching for the telltale signs of gravitational microlensing, subtle distortions in starlight caused by the presence of massive, unseen objects lurking in the darkness. Computer simulations paint a cautiously optimistic picture. The Roman Space Telescope might detect dozens of rogue black holes each year, gradually building a statistical map of how many such objects populate our galactic neighborhood. Nevertheless, despite these technological advances, the fundamental uncertainty remains. These invisible predators are elusive and unpredictable. We are in essence engaged in a cosmic game of hide and seek, where unseen objects could at any moment end human civilization without any prior warning. The universe teems with billions of stellar mass black holes, most of them entirely dark and undetectable by conventional means, whose paths are shaped by gravitational interactions that predate our very existence on Earth. What keeps astronomers awake at night isn't the probability of imminent catastrophe, which remains exceedingly small, but the unsettling awareness that somewhere in the darkness between the stars, these invisible entities drift silently through space. They possess enough gravitational pull to potentially reshape entire solar systems, and we have only just begun to understand their true numbers, their destinations, and the moments when one might meander close enough to remind us of our fragile cosmic position. Our recent ability to prove that these dark, silent hunters exist is a milestone, yet it is only the beginning. The real challenge lies in deciphering how many of them are out there, where they are headed, and when one might arrive to demonstrate just how delicate our cosmic situation truly is. If these solitary stellar black holes represent only the small fry of cosmic predators, then what of the supermassive behemoth lurking at the very core of our galaxy? This colossal entity, known as the supermassive black hole, embodies a hunger so immense that it defies comprehension. At the center of the Milky Way resides Sagittarius A, a gargantuan black hole weighing approximately 4 million times the mass of our Sun. For most of human history, this cosmic leviathan remained hidden behind curtains of dust and gas, invisible to optical telescopes. Its presence was inferred only through the frenetic dance of stars whirling perilously close, tugged by its overwhelming gravitational influence. In 2022, the world's most ambitious astronomical project, the Event Horizon Telescope, finally captured a direct image of Sagittarius A, a glowing ring of superheated matter spiraling inward toward its event horizon, the boundary beyond which nothing can escape. To grasp the scale of this monster, imagine compressing 4 million suns into a region smaller than Mercury's orbit around the Sun. The gravitational field there is so intense that matter orbiting near the edge reaches speeds approaching 20% of the speed of light before vanishing into the abyss. Stars vent deep within the heart of our galaxy lies an entity so colossal that it challenges our very understanding of cosmic scale. Sagittarius, a star, a supermassive black hole whose mass is estimated to be approximately 4 million times that of our Sun. For most of human history, this galactic behemoth remained shrouded in secrecy, concealed behind vast clouds of interstellar dust and gas that rendered it invisible to optical telescopes. Yet despite its elusive nature, its influence was unmistakably evident, manifesting through the frenzied dance-like motion of stars orbiting perilously close to what must be a point of infinite density. These stellar whirls and swift movements served as indirect but compelling indicators of the black hole's presence, a cosmic predator lurking in the galactic core. It was only in the year 2022 that humanity's technological ingenuity finally pierced the veil of obscurity. The groundbreaking accomplishments of the Event Horizon Telescope, an array of radio telescopes working in unison, produced the first-ever direct image of Sagittarius, a star. This monumental achievement revealed a luminous, glowing ring of superheated matter spiraling inward, gradually succumbing to the black hole's inexorable pull at what is known as its event horizon, the boundary beyond which nothing, not even light, can escape. To grasp the staggering scale of Sagittarius, a star, imagine compressing an astonishing 4 million suns into a sphere with a radius smaller than the orbit of Mercury. Such an incredible concentration of mass generates a gravitational field so intense that matter venturing near the event horizon accelerates to speeds approaching 20% of the speed of light, disappearing forever into the depths of the singularity. Stars that venture too close to this abyss are torn asunder by tidal forces in a process known as tidal disruption. These violent events produce spectacular displays called tidal disruption flares, where stellar debris is stretched and heated, forming luminous accretion disks, bright swirling rings of matter before ultimately vanishing into the darkness. Yet amidst these cosmic dangers, there is a comforting truth. Sagittarius, a star, currently poses no immediate threat to Earth, situated roughly 26,000 light-years away. Our solar system resides safely in the galactic suburbs, far removed from the chaos and cataclysmic activity at the galactic center. The black hole's gravitational influence does not extend to threaten our planet. It's not some cosmic vacuum cleaner indiscriminately devouring everything in its vicinity. Nor does it have the capacity to suddenly wake up and swallow Earth whole. However, it is important to recognize that Sagittarius A star has not always maintained its current tranquil state. Evidence from the recent cosmic past indicates that it has experienced episodes of intense activity, during which it emitted enormous bursts of high-energy radiation and left behind traces detectable even today. The most striking of these traces come from observations made by the Fermi Gamma Ray Space Telescope, which uncovered enormous bubble-like structures, known as the Fermi bubbles, extending roughly 50,000 light-years above and below the galactic plane. These colossal formations resemble cosmic exhaust plumes, remnants of titanic outbursts that occurred between 2 and 4 million years ago, spewing energized gas into the surrounding space. What could have driven such violent episodes? The answer lies in the feeding habits of supermassive black holes. Currently, Sagittarius A star is relatively starved, with little matter available nearby to consume. Yet, from time to time, the black hole's hunger is temporarily sated when gas clouds, disrupted stars, or even smaller black holes drift into its gravitational sphere of influence. These infrequent dramatic infusions of matter can trigger spectacular outbursts, during which the black hole transitions from its dormant state to a phase of intense activity, akin to becoming a quasar, the most luminous objects in the universe. If Sagittarius A star were to suddenly switch from quiet to full quasar mode, its radiation output could increase by factors of thousands or even millions, bathing the surrounding cosmos in a blinding flood of high-energy radiation. While the vast distance separating Earth from the galactic core provides significant protection, such an outburst, if it were to occur, would nonetheless have profound implications. Our solar system might be exposed to unprecedented levels of energetic radiation, a surge that could influence planetary atmospheres, disrupt communications, and potentially have subtle yet far-reaching effects on Earth's environment. Fortunately, under current conditions, Sagittarius A star remains in a relatively quiescent or dormant state, an enormous cosmic titan, but one that is not actively endangering the delicate balance of life on our planet. The immediate consequences of such an event would largely remain unseen by human eyes. Unlike dramatic displays of cosmic fireworks, phenomena like cosmic rays and gamma radiation do not produce brilliant light shows upon reaching Earth's atmosphere. Instead, their effects unfold subtly over extended periods. The increased radiation levels could gradually influence our planet's climate and atmospheric chemistry, instigating changes that are subtle yet potentially profound in their long-term impact. These processes involve physics that challenge our current understanding, complex, intricate mechanics that push the boundaries of human scientific knowledge. As matter spirals inexorably toward a supermassive black hole, it forms an accretion disk, a swirling luminous ring of heated material. The intense gravitational forces heat this matter to billions of degrees, creating conditions so extreme that they defy everyday comprehension. Magnetic field lines threading through this blazing disk can become twisted and energized, generating powerful jets of particles traveling at speeds approaching that of light. These jets act as narrow, focused beams of energy, stretching across thousands of light-years through the galaxy. Should Earth happen to align with one of these energetic outflows during an active phase, the potential consequences could be far more devastating than the diffuse radiation emitted by more common cosmic phenomena such as quasars. Recent observations utilizing the formidable capabilities of the Event Horizon Telescope have already begun to reveal that Sagittarius A star, the supermassive black hole residing at the center of our galaxy, is showing signs of a complex structure in its immediate environment. Polarized light measurements suggest intricate magnetic field arrangements encircling the black hole, the same kinds of fields that, under particular conditions, could launch formidable jets of matter and energy. While Sagittarius A star remains relatively quiescent at present, these magnetic configurations serve as a warning that the black hole still harbors the potential for far more dramatic activity. The timescales over which such supermassive black holes vary are staggering, ranging from minutes to millions of years. Currently, Sagittarius A star exhibits small-scale flares, brief bursts of increased luminosity occurring over hours as tiny amounts of matter cross the event horizon. However, the colossal outbursts that may have sculpted features like the Fermi bubbles, vast gamma-ray emitting structures extending above and below the galactic center, occur over much longer periods. These significant feeding episodes could last hundreds of thousands of years, fueled by the chaotic inflow of gas, stars, or even smaller black holes. The precise triggers for these major accretion events remain a subject of ongoing scientific investigation. Advanced computer simulations propose several plausible scenarios. One involves the disruption of massive star clusters orbiting near the galactic core, whose gravitational interactions could send vast quantities of matter spiraling inward. Another possibility is the capture and merger of intermediate mass black holes, smaller black holes that drift close enough to be swallowed by Sagittarius A star. Lastly, the collision or interaction of gas-rich dwarf galaxies with our own could funnel enormous streams of material into the black hole's grasp. Any of these cosmic encounters has the potential to ignite a quasar-like outburst, unleashing an energetic release that could temporarily transform our galaxy into a luminous active nucleus. Contemplating the psychological implications of living with a black hole containing the mass of about 4 million suns at the heart of our galaxy is a fascinating exercise. For most of human history, the existence of Sagittarius A star was entirely unknown, hidden behind thick clouds of dust and gas, its presence inferred only indirectly, if at all. Now, with direct imaging of its shadow and detailed observations of its environment, our cosmic perspective has shifted dramatically. We are effectively living in a galaxy armed with a loaded gun capable of firing a devastating burst at any moment. Yet paradoxically, this knowledge provides a peculiar form of reassurance. Sagittarius A star has persisted in a roughly steady state for billions of years. During this time, our solar system has completed countless orbits around the galactic center, enduring whatever radiation environment the black hole's activity has created. This enduring stability suggests that, while the threat remains real and ever-present in cosmic terms, the galaxy has operated under these conditions long enough that life on Earth has adapted and survived against these odds. The quiet patience of Sagittarius A star, its restraint over cosmic epochs, becomes a source of strange comfort, emphasizing that even the most formidable of cosmic monsters can coexist with the delicate existence of planetary life over vast spans of time. Life on Earth has, over eons, adapted to thrive within a universe that is far from tranquil, a galaxy animated by the relentless activity of its central supermassive black hole, Sagittarius A star. In a very tangible sense, our very existence has been shaped by these cosmic conditions. We are, after all, creatures born into a galaxy where the core is an active, dynamic engine of immense power and influence. Yet the true nature of this relationship isn't rooted in whether Sagittarius A star might one day awaken from its dormant state, an almost certain expectation given enough cosmic time, but rather in the uncertainties surrounding when such activity could resume and what form it might take. The scale of this black hole's activity stretches across cosmic epochs, vast periods that dwarf the entire span of human civilization. What might seem like a sudden burst of energy or a flare from our perspective could, from the galaxy's viewpoint, unfold over thousands of generations, an event occurring so gradually that it's almost imperceptible on any human timescale. Despite this, modern astronomy has equipped us with extraordinary tools and techniques that allow us to observe our galactic heart with unprecedented clarity and precision. Radio telescopes, for instance, meticulously track the orbits of stars in close proximity to Sagittarius A star, searching for subtle signs of disruption or perturbation that could signal an escalation in activity. Meanwhile, space-based observatories operating in the X-ray and gamma-ray spectra continually monitor the black hole's current emissions, vigilantly scanning for any anomalies or shifts that might indicate the onset of an active phase. They serve as our cosmic sentinels, ever watchful for the faintest hint that the sleeping giant might stir once more. Yet perhaps the most unsettling aspect of Sagittarius A star isn't merely the prospect of future outbursts or increased activity. It is instead a stark reminder of the fundamental organization of our galaxy. A system that is, in a very real sense, centered around this formidable gravitational behemoth. Every star in the Milky Way, including our own sun, follows an orbit dictated by the gravitational influence exerted by this central supermassive black hole. In essence, our entire galaxy's structure and dynamics are woven into the fabric of this gravitational system. We don't just live near a black hole, we exist within a galactic architecture that fundamentally depends on it. An invisible but omnipresent force shaping the cosmic neighborhood we inhabit. This realization leads us to ponder the broader cosmic landscape. What if the threat posed by Sagittarius A star is merely a distant echo of larger, even more formidable dangers lurking across intergalactic space? What other cosmic giants far more massive and energetic might exist beyond our galaxy, capable of unleashing destruction across vast distances and even across the voids separating galaxies? In the realm of these colossal phenomena, the universe's most formidable artillery serves as both a testament to cosmic power and a potential source of existential peril. Among these are neutron star collisions, magnetars, and gamma-ray bursts, cataclysmic events so energetic that they can be detected from billions of light-years away. These phenomena are capable of releasing in mere seconds more energy than our sun will emit over its entire 10-billion-year lifespan. Take, for example, the momentous event of August 17th, 3IATLAS, an unprecedented milestone for humanity. On that day, astronomers observed the collision of two neutron stars, an event detected simultaneously by gravitational wave observatories and optical telescopes. This groundbreaking detection, designated GW-177,817, marked the dawn of a new era known as multi-messenger astronomy, a field that combines the ripples in space-time with the light emitted from these cosmic cataclysms. Neutron stars themselves are among the universe's most extreme objects, compressed to densities that seem almost incomprehensible. A teaspoon of material from a neutron star would weigh as much as Mount Everest. Over millions of years, two such objects can spiral inward, driven by gravitational waves that stretch and squeeze the fabric of space-time itself. When they finally merge, a process that can take eons, they unleash gravitational waves racing outward at the speed of light, rippling through the universe's very structure. But the electromagnetic fireworks accompanying this final act are equally astonishing. The collision generates a kilonova, an explosion so luminous that it outshines entire galaxies for weeks. This event not only produces a spectacular light show, but also forges heavy elements, such as gold, platinum, and uranium, in quantities vastly exceeding what ordinary stellar processes can create. These elements are then scattered across the cosmos, enriching the universe and eventually becoming part of planets, life, and perhaps even ourselves. This extraordinary confluence of gravitational and electromagnetic phenomena demonstrates the universe's capacity for both destructive power and creative alchemy. It reminds us that, within the vastness of space, some of the most significant events occur in the blink of an eye, yet their echoes resonate across cosmic history, shaping the very fabric of matter and energy that compose our world. The elements that adorn your jewelry, the shimmering gold and the gleaming platinum in your car's catalytic converter, were not formed on Earth but in the fiery crucibles of distant cosmic events. Specifically, they were likely forged during cataclysmic collisions between neutron stars billions of years ago. Explosive phenomena so powerful that they scatter their stellar debris across the vast expanse of the universe. In essence, we are, quite literally, composed of the remnants of stellar catastrophes, fragments of ancient stars that met their violent ends. But neutron stars do not always wait for collision. Some unleash their fury through more immediate, ferocious acts. These are known as magnetars, neutron stars endowed with magnetic fields so extraordinarily intense that they make Earth's magnetic shield seem feeble by comparison. Magnetars possess magnetic fields trillions of times stronger than that of our planet, and they occasionally experience violent starquakes, sudden fractures in their crusts, that release staggering amounts of energy in mere milliseconds. To put this into perspective, these brief but monumental bursts of energy surpass the total output of our sun over hundreds of thousands of years. These colossal flares generate short gamma-ray bursts, intense focused pulses of high-energy radiation that can be detected across cosmic distances, piercing through the darkness of space with a brilliance that defies everyday experience. The physics underpinning these phenomena are so extreme that they challenge our understanding of matter and energy, operating in realms far beyond ordinary human intuition. The magnetic fields of magnetars are so overpowering that, at distances of mere thousands of kilometers, they would be lethal to humans. Not because of radiation, but because the magnetic field itself would interfere with biological electrical activity. This magnetic force is so strong it can distort the very shape of atoms, creating exotic states of matter that likely exist nowhere else in the universe outside the dense cores of neutron stars. When a magnetar erupts in a flare, it briefly becomes the brightest object in its galactic neighborhood, outshining countless stars in a flash of cosmic fury. One of the most dramatic events in recent history occurred in December of 2004. When a giant flare erupted from the magnetar designated SGR 1826. In less than a tenth of a second, this burst released more energy than our sun will produce over the course of 100,000 years. The intensity was so overwhelming that it temporarily blinded gamma-ray satellites orbiting Earth and caused detectable disturbances in our planet's ionosphere, despite originating on the opposite side of the galaxy, 50,000 light-years away. This event alone exemplifies the sheer scale of cosmic power at play. Mathematically, these phenomena become profoundly unsettling. Advanced computer models suggest that if a magnetar flare were to occur within approximately 30 light-years of Earth, it could strip away a significant portion of our planet's ozone layer, exposing the surface to lethal levels of ultraviolet radiation. At distances of 10 light-years or less, Such an event might trigger mass extinctions comparable to some of the most devastating episodes in Earth's deep geological past. Fortunately, astronomers have yet to identify any magnetars in our immediate cosmic vicinity. The closest confirmed magnetar resides over 9,000 light-years away, still within our galaxy but far enough to mitigate the threat of direct impact. Detecting neutron stars, including magnetars, remains a formidable challenge because they are often invisible unless actively emitting radiation. The universe is thought to be teeming with billions of these dense remnants scattered throughout the galaxy, most hidden from our view. The most concerning are the long gamma-ray bursts, death screams of the universe's most massive stars. When a star more than 25 times the size of our Sun reaches the end of its life. Unlike a typical supernova which disperses its material gradually, these colossal stars do not explode in a gentle burst. Instead, their cores collapse directly into black holes, launching narrow jets of material at nearly the speed of light, carving out cosmic beams of destructive energy that can be observed across the universe. These events are not only spectacular but also potentially catastrophic, especially if one of these jets were to be aimed directly at Earth. The powerful jets emanating from black holes, meticulously focused into narrow beams by the extreme physics near their event horizons, produce some of the most energetic and cataclysmic explosions known in the universe. These gamma-ray bursts, or GRBs, are among the most formidable phenomena, with their potential lethality depending critically on their energy output and the precise orientation of their emission. Atmospheric modeling suggests that if such a burst were to occur within just a few thousand light-years of Earth, directly aimed at us, it could trigger widespread destruction, including severe ozone layer depletion and significant climate upheaval. Although the burst itself would last only from a few seconds to a few minutes, its repercussions on Earth's atmosphere could linger for years, causing long-term ecological and biological disruptions. What makes gamma-ray bursts particularly terrifying isn't solely their staggering energy output, it's their complete unpredictability. Unlike supernova, which astronomers can sometimes anticipate based on the characteristics of their progenitor stars, GRBs seem to happen randomly across the cosmos with no warning signals beforehand. The first indication of such an event would be the arrival of intense gamma rays, traveling at the speed of light, leaving us with virtually no time to prepare or respond. Modern gamma-ray astronomy has revealed that these cosmic catastrophes occur roughly once every day somewhere in the observable universe. A sobering reminder of just how violent and perilous the universe truly is. Fortunately, the very properties that make gamma-ray bursts so energetic, namely their highly focused jets, also work in our favor. These jets are typically only a few degrees wide, meaning that even a relatively nearby burst would need to be precisely aimed at Earth to pose a threat. The odds of such a finely tuned orientation happening are exceedingly small, which provides a measure of reassurance. Our ability to detect and monitor these phenomena has advanced dramatically. The growing network of sophisticated instruments, including NASA's Fermi Gamma Ray Space Telescope, the Swift Observatory, and ground-based gravitational wave detectors like LIGO, Virgo, and CAGRA, collaborate seamlessly to provide real-time alerts when a gamma-ray burst is detected. Within minutes of an initial detection, astronomers around the world can swiftly direct optical, radio, and other telescopes toward the source, capturing the afterglow, the fading emissions that follow the initial explosion, and gaining invaluable insights into the physics behind stellar death and cosmic violence. This multi-messenger approach, combining gamma rays, gravitational waves, optical light, and radio signals, has revolutionized our understanding of the universe's most energetic events. No longer are we limited to studying these explosions through a single form of radiation. Instead, we now compile a comprehensive picture, revealing the complex processes that unfold when the universe unleashes its full fury. When considering the frequency of such events relative to their potential consequences, a pattern of both reassurance and concern emerges. The most powerful and far-reaching gamma-ray bursts, those capable of impacting Earth from great distances, are also the rarest occurrences. For example, magnetar giant flares, which are incredibly intense bursts of gamma rays and X-rays, happen perhaps once every century in a typical galaxy. Nearby gamma-ray bursts capable of damaging the Earth's biosphere are estimated to occur only once every few 100 million years. Despite their rarity, the universe's vastness ensures that such catastrophic events are not impossible. It contains hundreds of billions of galaxies, each hosting billions of stars at various stages of their life cycles. Somewhere within this immense cosmic expanse, neutron stars are colliding, magnetars are flaring with ferocious intensity, and massive stars are launching gamma-ray bursts, often directed toward unseen regions of space without warning or detectable signs. These silent, powerful explosions serve as stark reminders of the universe's capacity for destruction, lurking in the shadows, waiting to unleash their fury on unsuspecting worlds. The remarkable ability to detect these celestial phenomena from billions of light-years away stands as a profound testament both to the astonishing power these events unleash and to the extraordinary sophistication of the instruments humanity has crafted for cosmic observation. These tools, advanced telescopes, sensitive detectors, and intricate arrays, allow us to peer into the depths of space and time, capturing signals that have traversed unfathomable distances before reaching our vantage point on Earth. Such detection not only underscores the immense energy involved in these cosmic giants, but also highlights the incredible progress we've made in understanding the universe's most violent and awe-inspiring phenomena. What makes these colossal events particularly disconcerting, however, is their profound role as cosmic regulators of habitability. A gamma-ray burst, an intense, narrowly focused emission of high-energy radiation, originating from a sufficiently close and precisely aimed source, could sterilize the entire surface of our planet without any forewarning. This catastrophic burst of radiation has the potential to wipe out all surface life, effectively resetting Earth's evolutionary progress and forcing any surviving organisms to start anew from the most primitive forms of life. In this light, these stellar phenomena serve a kind of cosmic quality control mechanism, periodically sweeping through the universe and eliminating planets teeming with complex life forms. Such events act as natural gatekeepers, ensuring that intelligence remains an exceedingly rare and precious commodity, preserved only in the most fortunate or shielded locations within the cosmos. Yet the thought of a future event, a sudden brilliant flash illuminating our sky, might not be the collision of distant neutron stars or the catastrophic collapse of a massive star alone. Instead, it could be something far more violent and unpredictable. The final, desperate scream of a star tearing itself apart in a last-ditch effort to achieve some form of cosmic immortality. This leads us to a provocative hypothetical scenario, the so-called false dawn star. A concept rooted in the realm of cosmic imagination but grounded in the physics of stellar death and black hole formation. Imagine awakening one morning to find the eastern horizon ablaze with a strange, unnatural light. A luminous spectacle that isn't the familiar sunrise we anticipate. This is a false dawn, an eerie and unsettling phenomenon that stretches across the sky, casting shadows in directions opposite to those of the real sun and painting the landscape with hues that defy description. Colors that have no name in our earthly palette. For a few terrifying seconds, this alien sunrise outshines the natural dawn. a blazing, unnatural glow visible even in broad daylight before gradually fading into a brilliant pinpoint of light that will linger in the sky, haunting the horizon for months to come. In that moment, you have just witnessed the death throes of a massive star, its final act, culminating in the birth of one of the universe's most terrifying phenomena. This scenario represents our third hypothetical doomsday, a distant but conceivable catastrophe. A nearby massive star collapsing into a black hole, unleashing a gamma-ray burst directly aimed at Earth. While the odds of such an event occurring are extraordinarily slim, akin to cosmic improbabilities, its potential consequences are so devastating that even seasoned astronomers, aware of the universe's violent nature, sometimes find themselves sleepless, contemplating the possibility. Gamma-ray bursts are among the universe's most violent explosions, embodying cosmic fury in its purest form. When a star, more than 25 times the mass of our Sun, reaches the end of its life, its core can undergo a rapid collapse so intense that no supernova explosion can halt the formation of a black hole. Instead, the infalling matter doesn't quietly vanish into oblivion. It forms a superheated accretion disk around the nascent black hole, setting the stage for the launch of powerful jets of material. These jets are expelled at velocities approaching the speed of light along the star's rotation axis, carrying more energy than our Sun will emit over its entire 10 billion-year lifespan, but concentrated into narrow beams just a few degrees wide. When one of these cosmic death rays, these gamma-ray bursts, sweeps through space in our direction, it manifests as an explosion so luminous that it can be observed from the very edge of the observable universe. The physics involved in such an event pushes the boundaries of what matter and energy are capable of accomplishing, defying our current understanding of the universe's fundamental laws. The gamma rays themselves are photons, particles of light, that carry millions of times more energy than visible light, and when they interact with Earth's atmosphere, they do not produce the gentle dancing auroras we see during solar storms. Instead, they unleash a destructive and relentless wave of high-energy radiation capable of devastating the delicate balance of life on Earth. Gamma-ray bursts possess the astonishing ability to trigger nuclear reactions high in our planet's atmosphere, setting off a chain of events that could have devastating consequences. When these intense bursts of gamma radiation strike Earth, they interact with atmospheric nitrogen and oxygen molecules, converting them into radioactive isotopes. This process critically damages the ozone layer, the delicate shield that safeguards us from the sun's harmful ultraviolet rays. Computer simulations modeling this atmospheric destruction reveal a stark and sobering reality. If a gamma-ray burst were to occur within just a few thousand light-years and be aimed directly at Earth, it could erode our ozone layer by 50% or more within mere seconds. The immediate effects of such an event would be virtually invisible to human observers. Unlike supernovae or bright meteor showers, gamma rays do not produce spectacular visual displays upon impact. They are invisible to the naked eye. Nevertheless, the aftermath would unfold over the following days or weeks, as the increased influx of ultraviolet radiation begins to penetrate the surface of our planet. The biological consequences would be gradual but profound, extending over months to years. Without sufficient ozone protection, ultraviolet light would seep deeper into the oceans, disrupting phytoplankton populations, the microscopic plants that form the foundational base of marine food webs. These tiny organisms are vital for oxygen production and carbon cycling. Their decline would threaten the entire marine ecosystem. On land, the rise in ultraviolet exposure would cause widespread DNA damage in plants and animals. This would lead to a surge in cancer rates, weakened immune defenses, and catastrophic failures in agriculture. Ecosystems already under stress from climate change or human activity would be pushed beyond their limits, risking potential collapse. What makes this scenario especially unsettling is the fact that there would be no warning signs before the event strikes. Unlike asteroid impacts, which we can often detect months or even years in advance, gamma-ray bursts travel at the speed of light. The first indication of such an event would be the gamma rays themselves reaching Earth, a signal that would be received within milliseconds by satellite-based detectors orbiting our planet. By the time we became aware of the burst, the atmospheric damage would already be underway. This phenomenon, referred to as the false dawn effect, would be profoundly terrifying for any humans witnessing it. For a few seconds or minutes, a gamma-ray burst originating from within our galactic neighborhood could appear as an extraordinarily bright object, a new star blazing in the sky, possibly outshining the full moon. To our ancestors, such an event would have seemed a divine omen, a sign from the cosmos. Today's astronomers recognize it as a potential harbinger of catastrophe, a warning of the universe's lethal power. Historically, scientists have identified several stars that could, in theory, produce gamma-ray bursts capable of threatening Earth. One such candidate was Wolf-Rayet's star Chicxulub, located roughly 8,000 light-years away. Its enormous mass and rapid rotation had made it a prime suspect, and it frequently topped lists of stars most likely to cause a global catastrophe. However, recent observations have cast doubt on this threat. New data suggests that Wolf-Rayet's Chicxulub's rotation axis is not aligned with our planet, significantly reducing the likelihood that any gamma-ray burst it might generate would be aimed directly at Earth. This highlights a crucial aspect of gamma-ray bursts, their geometry and the beaming effect. Gamma-ray bursts are highly directional phenomena, with their intense jets typically only 1 to 10 degrees wide. This means that for a nearby star to pose a direct threat, it would need to be precisely oriented so that its narrow jet points directly at Earth, an unlikely coincidence. Most gamma-ray bursts therefore sweep harmlessly through the cosmos, their lethal radiation dissipating into the vast emptiness of space. This beaming effect, while making these explosions incredibly energetic, works in our favor by greatly reducing the probability of Earth being directly in the line of fire. Consequently, although gamma-ray bursts are among the most powerful phenomena in the universe, their actual threat to our planet is mitigated by the narrowness of their jets and the random orientation of their sources in space. The timing and effects of gamma-ray bursts unfold across an extraordinary range of timescales, spanning from mere seconds to many centuries. The initial emission, the burst itself, typically endures for only a few milliseconds to several minutes. An incredibly brief yet immensely powerful flash of high-energy radiation that can momentarily illuminate the cosmos in a blinding display. This fleeting event unleashes a torrent of gamma rays so intense that it can have profound consequences for a planet's atmosphere and biosphere. In the days immediately following such an explosion, the atmospheric chemistry would reach its peak disruption. High doses of gamma radiation would break apart ozone molecules, causing a sharp depletion of this vital shield. Yet this destruction wouldn't be a transient phenomenon. It could linger for months or even years, as the natural recovery process of the ozone layer unfolds at a slow, painstaking pace. During this period, the planet's protective barrier would be significantly weakened, leaving the surface exposed to increased levels of ultraviolet radiation. The biological and ecological repercussions of such an event might extend well beyond the immediate aftermath, influencing life on Earth over decades, centuries, or even longer. The disruption to ecosystems, the collapse of food chains, and the potential for widespread extinctions could unfold gradually, shaped by the length of atmospheric recovery and the resilience of various species. Current scientific estimates suggest that gamma-ray bursts capable of causing widespread devastation in our galactic neighborhood are extraordinarily rare, occurring roughly once every few 100 million years. While this frequency might seem negligible in human timescales, it is frequent enough over geological epochs to have potentially influenced the evolutionary course of life on Earth. Some researchers have even hypothesized that these cataclysmic events could explain certain mass extinction episodes recorded in Earth's deep past, although concrete evidence remains elusive and highly speculative. As our understanding of stellar evolution and gamma-ray phenomena advances, astronomers have become increasingly sophisticated in their efforts to detect and monitor the stars most likely to produce such destructive bursts. Space-based observatories are tirelessly scanning known Wolf-Rayet stars and other massive stellar objects, diligently searching for signs of instability, such as sudden brightness fluctuations or spectral shifts, that might indicate an impending collapse into a gamma-ray burst. Ground-based surveys complement these efforts by hunting for new candidate stars, while theoretical models aim to identify which stars are most likely to end their lives with a lethal gamma-ray emission directed toward our planet. Despite these technological strides, the fundamental unpredictability inherent in stellar collapse remains a persistent challenge. The precise timing of when a massive star will explode, or whether it will do so at all, continues to elude scientists, rendering gamma-ray bursts a cosmic form of roulette. We can narrow down the most probable candidates and refine our atmospheric impact models with greater accuracy. Yet we remain powerless to prevent such an event once the star reaches its critical threshold. This unavoidable uncertainty raises significant psychological and philosophical questions. How does it feel to live in a galaxy where, somewhere, massive stars are quietly approaching the end of their lives, potentially harboring within them the power to reset civilization? For most people, these threats remain comfortably abstract, distant hazards that do not influence daily decisions because they are so rare and unpredictable. However, for astronomers and astrophysicists who study these phenomena professionally, this knowledge can be profoundly unsettling. An unsettling reminder of how little control humanity has over cosmic forces operating on scales far beyond our reach. The most troubling aspect of the gamma-ray burst scenario lies in its stark illustration of our technological fragility in the face of cosmic phenomena. Unlike asteroid impacts, which we are gradually learning to detect and potentially deflect through interventions like kinetic impactors or nuclear devices, a well-timed gamma-ray burst would leave us helpless. Our current technological infrastructure, no matter how advanced, would be as impotent as the dinosaurs against their asteroid impactor, an event that, in a matter of seconds or minutes, could wipe out much of Earth's surface life. There is, however, a faint glimmer of reassurance, if one can call it that, embedded in the rarity and randomness of such events. The universe is vast, containing billions of massive stars, yet only a tiny fraction of these will ever produce a gamma-ray burst, and among those, only an even smaller subset will direct their lethal emissions toward inhabited worlds. This extreme scarcity means that, statistically speaking, the likelihood of a gamma-ray burst threatening Earth in any given human lifespan remains exceedingly low. Nonetheless, the very possibility underscores the importance of continued vigilance and advanced monitoring, as even the rarest cosmic threats have the potential to reshape the destiny of life on our planet. The universe, with all its intricate and vast complexity, seems to have a remarkable propensity for favoring survival amid the chaos of stellar death and cosmic upheavals. Most of the time, the cosmic lottery that determines the fate of stars appears to be skewed in our favor, with catastrophic events like supernova or neutron star collisions happening at intervals that, while devastating on a local scale, rarely threaten the very fabric of existence on a universal scale. But what if the next great existential threat doesn't originate from the violent death throes of distant stars or violent collisions in the depths of space? What if the danger lies not in the fiery explosions or gravitational cataclysms we observe, but in the very foundation of reality itself? Imagine a wave, an immense hypothetical disturbance rippling through the fabric of space, so profound that it could fundamentally alter the very laws of physics as we understand them. This concept, known as the cosmic wave, represents our 10th and most speculative doomsday scenario, a thought experiment that challenges the limits of current scientific understanding and ventures into realms that would make even seasoned science fiction writers pause. To be perfectly clear from the outset, there is no credible scientific evidence to suggest that such cosmic waves exist or pose an imminent threat to Earth or life as we know it. Our exploration of this idea is purely within the realm of theoretical physics and worst-case scenario modeling. Nonetheless, the fact that some of the most respected physicists have seriously pondered such possibilities speaks volumes about how much remains unknown in our understanding of the universe. This idea of a cosmic wave emerges from our expanding awareness of dark energy, the mysterious force that seems to be accelerating the universe's expansion at an ever-increasing rate. When Albert Einstein first introduced his cosmological constant in 1917, he did so as a mathematical fudge, a static adjustment designed to prevent the universe from collapsing under its own gravity. He later famously called it his greatest mistake when subsequent observations revealed that the universe was not static but expanding. Yet, by the late 20th century, astronomers discovered something even more astonishing. This expansion was not just continuing but accelerating. This acceleration appears to be driven by some form of energy that permeates all of space, an enigmatic entity now known as dark energy, which constitutes approximately 68% of the universe's total mass energy content. Despite its dominant presence, dark energy remains one of the greatest mysteries in modern physics. We understand almost nothing about its true nature. Is it a fundamental property of space itself, an inherent characteristic woven into the fabric of the cosmos? Could it be a field that changes strength or direction over time, perhaps even fluctuating unpredictably? Might it be unstable under certain conditions, capable of triggering profound shifts in the universe's structure? These questions lead us into uncharted theoretical territory, where even our most advanced models and hypotheses offer limited guidance. Among the most intriguing yet highly speculative concepts is the idea of false vacuum decay. This notion suggests that the quantum fields governing the fundamental properties of matter and energy might exist in a delicate metastable state, a kind of cosmic ball balanced precariously on the edge of a hill, poised above a lower energy state. In this analogy, our universe inhabits a false vacuum, a local minimum of energy that appears stable but is actually susceptible to sudden change. If disturbed, perhaps by quantum fluctuations or interactions with as yet undiscovered fields, this metastable state could trigger a chain reaction, a cascade effect that would propagate outward at the speed of light, reshaping the very fabric of reality in its wake. This wave, should it occur, would not be composed of matter or energy in any familiar sense. Instead, it would represent a fundamental transition in the underlying structure of the universe, an upheaval so profound that the very laws of physics as we understand them could be rewritten instantaneously. The potential for such an event remains purely hypothetical, yet contemplating its possibility pushes the boundaries of our scientific imagination and underscores how little we truly comprehend about the deeper workings of the cosmos. Within the fabric of space-time, a domain where the very fabric of reality might behave in ways utterly alien to our current understanding, lies a realm of profound uncertainty. In such a hypothetical region, the fundamental laws of physics, those governing the behavior of atoms, forces, and matter, could operate under entirely different principles. Imagine a universe where atoms, the building blocks of everything we know, are unable to form, where the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, might fluctuate in strength or direction. In this scenario, the very concept of matter as we understand it could lose its meaning altogether, dissolving into a chaos of exotic phenomena governed by unfamiliar physics. The most unsettling aspect of this possibility isn't the vast amounts of energy that might be involved, but rather the sheer unpredictability of what would occur when such a wavefront arrived. Would all matter abruptly vanish into nothingness? Might it morph into strange alien forms that obey different laws, defying our capacity to comprehend or predict? Could conscious beings, observers capable of perceiving the universe, simply find their awareness obliterated or rendered impossible under these altered physical conditions? These questions evoke a profound sense of cosmic dread as they challenge the very fabric of reality and our place within it. Fortunately, the very physics that render such scenarios conceivable also indicate that they are exceedingly improbable in the natural universe. Quantum field theory, our most advanced framework for understanding the subatomic realm, suggests that events like false vacuum decay, hypothetical processes where our current state of the universe might suddenly transition into a different, more unstable state, are extraordinarily rare. If such decay events occur at all, their likelihood might be measured in terms of perhaps one occurrence per universe per cosmic age, a timescale so vast that it renders the event practically negligible. The energy barriers that safeguard our current vacuum state appear insurmountably high. They demand fluctuations of an intensity far beyond anything our current scientific models predict or can envisage. These barriers act as cosmic fortresses, preventing the spontaneous transition to a more unstable state. Additionally, our observations of the universe, particularly the detailed measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang, show no signs of irregularities or anomalies that would suggest an underlying instability. These measurements, spanning billions of years and billions of light-years across space, demonstrate that the universe operates under a remarkably consistent set of physical laws. If our universe's vacuum were truly fragile or on the brink of decay, we might expect to observe signs of such processes occurring elsewhere, perhaps in distant regions of the observable cosmos. The absence of such evidence lends weight to the idea that our current state is stable, at least within the scope of our empirical reach. The concept of cosmic waves, large-scale disturbances traveling through the universe's structure, intersects with our understanding of the cosmic web, the vast network of filaments and voids that make up the universe's large-scale structure. On scales of hundreds of millions of light-years, matter is organized into intricate patterns of galaxies and dark matter separated by immense voids. In this grand cosmic tapestry, shock waves and pressure fronts do propagate, resulting from the collision and merging of galaxy clusters. Yet these are well understood phenomena involving the movement of ordinary gas and dark matter, rather than fundamental alterations of physical laws. Certain speculative theories in advanced cosmology, however, do entertain the possibility of more exotic scenarios. For instance, some brain world models propose that our universe might exist as a membrane, or brain, embedded within a higher dimensional space. Such models entertain the idea that interactions or collisions with other brains could cause radical shifts in physical laws, potentially triggering catastrophic changes. Similarly, string theory's landscape of possibilities presents a vast array of potential vacuum states, each characterized by different physical constants and particle properties. While these theories are tantalizing and extend the boundaries of our scientific imagination, they also underscore the importance of responsible scientific inquiry. The line separating legitimate theoretical speculation from unfounded alarmism can be surprisingly thin. Today, the internet is replete with claims about imminent cosmic threats, so-called cosmic waves or other phenomena. often based on misinterpretations of complex scientific papers or outright fabrications designed to attract attention, clicks, and views. And quote, these unfounded claims can stoke unnecessary fear, divert attention from real scientific exploration, and distort the public understanding of the universe's true nature. While scientific theories about the universe's potential instabilities are vital to advancing our understanding, it is equally crucial to approach such ideas with rigorous skepticism and careful analysis, ensuring that speculation does not becloud the empirical evidence that currently attests to the universe's remarkable stability. Distinguishing between rigorously peer-reviewed scientific research and the more speculative narratives often found in platforms like YouTube requires meticulous scrutiny of sources and methodologies. The scientific community has established a multitude of methods to assess the stability of our universe's current vacuum state, an essential pursuit given its profound implications for cosmic fate. For instance, particle accelerators such as the Large Hadron Collider serve as vital tools in probing the behavior of fundamental fields at extremely high energies. These experiments seek signs of potential instability or phase transitions that could signal a shift in the vacuum stability, thus threatening the fabric of our universe. Complementing these laboratory efforts are cosmological observations, which meticulously monitor the cosmic microwave background and analyze the large-scale structure of the universe for anomalies. Such anomalies could hint at vacuum decay events occurring elsewhere in the cosmos, offering indirect evidence of shifts in the underlying physical laws. To date, all observational data bolster the conclusion that our universe operates under a set of stable physical laws that have remained remarkably consistent across the immense expanses of cosmic time. The fundamental constants, parameters such as the speed of light, gravitational constant, and electron charge, appear to be truly invariant, with no detectable signs of decay or variation. Likewise, the quantum fields that determine particle masses and the strengths of fundamental interactions show no evidence of instability. Contemplating the existence of cosmic waves, hypothetical disturbances that could ripple through space-time and alter the fabric of reality, operates on scales and time frames that far surpass human civilization's lifespan. The psychological impact of these scenarios is significant, acknowledging the possibility that such fundamental threats could undermine the very foundation of physical existence is inherently unsettling. Unlike threats that destroy matter or energy within the known laws of physics, these existential risks threaten to redefine the very nature of reality itself. While we can conceptually imagine surviving asteroid impacts, radiation exposure, or climate shifts, the idea of existence persisting under radically different physical laws is profoundly challenging to grasp. Yet, this very discomfort reveals something intrinsic to human nature: a deep-seated confidence in the stability and intelligibility of the universe. The fact that cosmic wave scenarios feel so alien and threatening suggests that we have evolved in a universe characterized by genuine stability, where the laws of physics have persisted long enough to give rise to galaxies, stars, planets, and life itself. Perhaps the most profound lesson to glean from cosmic wave speculation is one of humility, an acknowledgement of our limited understanding despite centuries of scientific progress. Dark energy, the mysterious force accelerating universal expansion, remains largely unexplained. Quantum gravity, the elusive theory uniting general relativity and quantum mechanics, continues to challenge our most advanced theories. The relationship between consciousness and the laws of physics remains an enigma, entirely opaque to current scientific methods. This enduring mystery is precisely why many believe we should approach these questions with gratitude rather than fear. The universe has provided a remarkably stable platform, an environment in which complexity, discovery, and wonder have flourished. It has remained consistent long enough for intelligent life to emerge and to begin questioning its own origins and destiny. As of now, the hypothetical cosmic waves we ponder have not yet reached our corner of space-time. They remain distant beyond the horizon of current detection and understanding. Ultimately, the most honest response to these scenarios is one of awe, an appreciation for the universe's intricate complexity and delicate balance, which has allowed us to exist and contemplate our place within it. Gratitude emerges naturally for the remarkable stability that has persisted, enabling life and consciousness to flourish amidst the vast cosmic backdrop. Far from inducing fear, this perspective encourages humility and reverence for the profound mysteries still awaiting discovery in the depths of the universe. If the universe were fundamentally unstable at its core, threatening to unravel the very fabric of space-time, then surely we wouldn't be here pondering such questions at all. Evolution, life, consciousness, all of it would be impossible in a cosmos prone to chaos and collapse. Yet if the universe's underlying laws are stable, consistent, and benevolent, if space-time isn't actively hunting us and the fundamental physics remain unchanging, then perhaps our greatest dangers are not lurking outside but within. Not from hostile celestial entities intent on our destruction, but from other forms of intelligence that have learned how to navigate the cosmic perils far more effectively than we ever could. This is the core of what's known as the Fermi paradox, a question that first emerged in Odna Tisica Davidsot Patdisat during a casual lunchtime discussion at Los Alamos National Laboratory, when physicist Enrico Fermi asked, "Where is everybody?" This straightforward query has since become a haunting puzzle for astronomers, philosophers, and scientists alike. His reasoning was deceptively simple. Considering the vastness of the universe with its staggering age and the countless stars and planets it contains, where are all the extraterrestrial civilizations? The universe is approximately 13.8 billion years old, long enough for intelligent life to have emerged, evolved, and perhaps even mastered interstellar travel multiple times over. Our galaxy alone, the Milky Way, hosts an estimated 400 billion stars. Recent discoveries made by the Kepler Space Telescope and other planet-hunting missions suggest that planets similar in size to Earth, orbiting within the habitable zones of their stars, are surprisingly common. Even adopting conservative estimates, this implies there could be billions of potentially hospitable worlds just within our galaxy. Now expand this perspective to the entire observable universe, which contains roughly 2 trillion galaxies, each with its own multitude of stars and planets, and the scale becomes almost incomprehensible. The numbers are so immense that they challenge our ability to grasp their significance. Given such staggering figures, the apparent silence of the cosmos becomes even more perplexing. Despite decades of searching, sending out radio signals, scanning the skies for signs of artificial megastructures, listening for alien transmissions, we have yet to find any definitive evidence of extraterrestrial intelligence. No unmistakable radio signals that defy natural explanations, no alien civilizations building structures that block starlight, no signs of industrial pollution on distant worlds. The universe, as it appears, is an eerily quiet library with no other readers. This silence manifests in 2 troubling ways, each with its own disturbing implications. The first is the absence of visitation. No alien ships have landed on Earth. No probes have made contact, despite the tantalizing possibility that extraterrestrial life could have reached us by now. This is despite widespread speculation fueled by sensational headlines suggesting otherwise. The second, perhaps even more confounding, is the total lack of detectable signals or signatures of advanced technological civilizations in our local cosmic neighborhood. Our efforts to detect extraterrestrial intelligence, though impressive compared to what was possible in the past, remain limited in scope and sensitivity. The search projects have scrutinized only a tiny fraction of nearby stars, and only within narrow slices of the electromagnetic spectrum, those frequency bands we assume might be used for interstellar communication. Despite these constraints, the silence persists, raising profound questions about our place in the universe. Are we truly alone? Are we among the first, the early bloomers of intelligence? Or are we being deliberately avoided or overlooked? Or perhaps, we're simply searching with the wrong tools in the wrong places at the wrong times. The numbers involved amplify the puzzle. With over 400 billion stars in our galaxy alone and the growing evidence that Earth-like planets are common, the likelihood of extraterrestrial life seems high. When we scale this up to the universe's estimated 2 trillion galaxies, the odds become almost unfathomable. Yet, despite these probabilities, our detectors remain silent, and the universe's vast expanse continues to seem empty. An enormous cosmic stage where no other intelligent actors are making their presence known. We are, in essence, attempting to listen in on cosmic dialogues with methods that are scarcely more advanced than the primitive radio technologies available to Marconi at the dawn of wireless communication. The communication systems of truly advanced extraterrestrial civilizations might employ techniques and technologies that are beyond our current imagination, possibly involving quantum entanglement, neutrino signals, or other phenomena that defy our understanding. This adds an intricate layer to the temporal aspect of the Fermi paradox, the profound question of why, given the vastness and age of the universe, we have yet to detect clear evidence of other intelligent life. Human civilization, by comparison, has been technologically sophisticated for just a few centuries, an almost fleeting moment in cosmic terms, a mere blink of an eye in the grand timeline of the universe. Radio astronomy, which is the primary tool we use to seek out extraterrestrial signals, has been in existence for less than a century. Our active search for signals from other civilizations has only been ongoing for a few decades. If such civilizations tend to be short-lived, lasting only a few centuries or perhaps a few thousand years before they self-destruct through war, environmental disasters, or technological overreach, the probability that 2 such civilizations exist simultaneously, overlapping in both space and time, diminishes drastically, approaching near impossibility. The vast scales of space and time involved further compound this challenge. For example, light from our nearest star takes over 4 years to reach us, meaning we are looking back in time over 4 years with every observation. A radio signal sent from the galactic center, located approximately 26,000 light-years away, would require that same span of time to arrive here. To put this into perspective, if an alien civilization had begun broadcasting a message of greeting during the construction of the Egyptian pyramids, that message would only now be reaching star systems that are 5,000 light-years distant. The immense cosmic distances and the slow pace of light travel make the chance of 2 civilizations overlapping in both space and time exceedingly slim, almost negligible. This leads to what researchers term the Great Filter Hypothesis, a concept proposing that there is some critical evolutionary or technological barrier that prevents most life forms from progressing to a stage where they become detectable spacefaring civilizations. The filter could be situated in our distant past, perhaps at the point where life first emerged, or at the stage of developing complex cells or intelligence, which might be far rarer than previously assumed. Alternatively, the filter might lie ahead of us, suggesting that civilizations tend to destroy themselves through war, environmental catastrophe, or other self-inflicted disasters before they can become persistent, detectable entities on a galactic scale. The idea that the Great Filter might still be in our future is particularly unsettling, implying that the evolution of intelligence could be inherently self-destructive. If the inevitable outcome of advanced intelligence is self-destruction, then our current technological state might not be the beginning of a cosmic conversation, but could represent the final chapter of terrestrial civilization. Every nuclear weapon we produce, each increase in global temperature caused by human activity, and every potentially dangerous technological pursuit could be steps toward the same fate that silences countless other civilizations, an extinction driven by our own hand. However, there are other plausible explanations that do not assume civilizations inevitably perish. Perhaps, out of caution or wisdom, advanced extraterrestrial societies choose to remain deliberately silent, understanding that revealing their presence might attract the attention of hostile neighbors or predatory civilizations. They might have progressed beyond electromagnetic communication altogether, developing new methods rooted in quantum entanglement or other phenomena that are still beyond our grasp. Moreover, it's conceivable that some of these civilizations are already here, observing us with such sophisticated camouflage and stealth technology that their presence remains entirely undetectable, hidden behind layers of technological deception, silent and unseen. Modern strategies in the search for extraterrestrial intelligence have evolved significantly beyond the traditional approach of merely listening for radio signals. Today, astronomers are actively seeking techno-signatures, indirect indicators of advanced technological activity that might be detectable across the vast expanses of interstellar space. These efforts include the search for artificial structures, megaconstructs, or engineered objects that could partially obscure or block the light from distant stars, hinting at the presence of intelligent civilizations building their habitats or energy sources. Scientists also analyze the atmospheres of exoplanets for signs of industrial pollutants, chemical byproducts that suggest industrial processes or technological pollution, clues that may reveal the existence of civilizations far beyond our solar system. Additionally, researchers monitor for brief, intense laser pulses, sharp flashes of light that could be interstellar communication signals or beacons, trying to catch the subtle echoes of deliberate attempts at contact. A recent focus of SETI, Search for Extraterrestrial Intelligence efforts, has been on fast radio bursts, mysterious millisecond-long pulses of radio energy originating from distant galaxies. These brief, powerful flashes exemplify both the immense potential and the frustrations of current SETI research. When these signals were first detected, some scientists speculated they might be evidence of alien technology, perhaps artificial signals intentionally transmitted by extraterrestrial civilizations. However, more detailed and rigorous analyses have since demonstrated that these bursts are almost certainly natural phenomena, most likely produced by highly magnetized neutron stars known as magnetars, which emit intense bursts of electromagnetic energy during their violent magnetic activity. The fact that we even considered the possibility of artificial origins for these signals underscores how deeply humanity desires to find evidence that we are not alone in the universe. Our curiosity and hope drive us to interpret even ambiguous signals as potential signs of extraterrestrial intelligence. Yet this tendency reveals a bias, the tendency towards anthropocentric thinking that might be limiting our search strategies. We tend to look for signals and phenomena similar to those we produce ourselves, using technologies and operating on timescales familiar and reasonable to us. We search for radio signals, laser flashes, and technological signatures that mirror our own methods of communication and energy use. However, it's entirely possible that highly advanced civilizations communicate using forms of technology and on scales vastly different from ours, such as gravitational waves, quantum manipulation, or processes occurring over geological time spans that dwarf human history. Such civilizations might operate on principles and durations completely alien to our understanding, making their signals undetectable with our current tools and assumptions. For example, they could harness gravitational waves, ripples in space-time, as a means of communication or manipulate matter at the quantum level in ways that produce no detectable electromagnetic signature. The Drake equation, formulated in the early 1960s by Frank Drake, remains a philosophical framework rather than a precise predictive tool. It attempts to estimate the number of intelligent communicative civilizations in our galaxy based on variables such as the rate of star formation, the fraction of stars that host planets, and the probability of life emerging. Despite decades of astronomical progress, these variables are still poorly constrained, leaving the equation's predictions highly uncertain. Depending on the assumptions plugged into the Drake equation, the results range from the unsettling conclusion that humanity might be alone in the universe to the optimistic possibility that millions of civilizations could be out there, waiting to be discovered. Perhaps the most profound implication of the Fermi paradox, the apparent contradiction between the vast number of potentially habitable worlds and the total lack of evidence for extraterrestrial civilizations, is not about extraterrestrials at all. Instead, it is a reflection of our own existential responsibility. The silence of the universe places an enormous moral and philosophical burden on humanity. If intelligent life is exceedingly rare, then our own consciousness and civilization might be a rare and precious flowering of awareness in an otherwise silent and inert cosmos. This realization compels us to consider the importance of preserving and protecting human civilization, for it may be one of the few, if not the only, examples of consciousness in the universe. Nevertheless, this same silence also raises a disturbing possibility that we are approaching a filter, a cosmic threshold that has already silenced or wiped out other civilizations before they could become detectable. This filter might be the natural, self-imposed, or inevitable barrier that prevents civilizations from surviving long enough to communicate across the stars. Every global crisis, climate change, nuclear proliferation, unchecked development of artificial intelligence, or biotechnological risks, takes on a new weight when viewed through the lens of the Fermi paradox. Our collective future, and perhaps the future of intelligence itself, could be at risk of crossing this cosmic threshold, leading to self-destruction or silence. In essence, the silence of the universe is not merely an absence of signals. It is a mirror reflecting the profound responsibilities and potential peril faced by human civilization. It underscores the importance of cautious progress and the need for wisdom in navigating the technological and ecological challenges ahead. As we continue to explore, the paradox further compels us to contemplate a profound and unsettling possibility: that consciousness itself may be far more rare and delicate than our natural assumptions lead us to believe. We often take our own awareness for granted, assuming it to be a commonplace feature of intelligent life. However, the emergence of subjective experience, our inner feeling of being aware, remains one of science's most significant and elusive mysteries. Despite centuries of philosophical debate and scientific inquiry, it still resists a comprehensive explanation, leaving us to wonder whether consciousness is a rare gem among cosmic phenomena or a fragile phenomenon easily lost. If indeed consciousness is an extraordinary rarity across the universe, then its preservation takes on cosmic importance beyond mere curiosity. The survival of conscious beings, those capable of reflection, innovation, and understanding, may be an imperative for the universe itself, a fragile spark that needs safeguarding amidst the vast emptiness. Recent advances in astrobiology have added compelling new layers to the long-standing Fermi paradox, which questions why we have yet to encounter evidence of extraterrestrial civilizations despite the universe's apparent abundance of habitable worlds. Discoveries of potentially life-supporting exoplanets such as Proxima Centauri b, TRAPPIST-1e, and Kepler 452b have demonstrated that worlds similar to Earth are not just theoretical possibilities but are present in our cosmic vicinity. These planets, orbiting stars within a few light years or a few dozen light years away, suggest that the universe is filled with planetary environments that could foster life. The upcoming capabilities of the James Webb Space Telescope promise to analyze the atmospheres of these distant worlds in unprecedented detail, potentially revealing signs of biological activity, such as oxygen, methane, or other biosignatures, that could hint at the presence of life beyond Earth. Yet, even if we detect signs of life, the question of intelligence remains largely unanswered. The leap from simple life forms to intelligent, technologically capable civilizations is vast and uncertain. The search for extraterrestrial intelligence, SETI, continues to grow in scope and sophistication. New radio telescope arrays like the Square Kilometer Array are poised to provide extraordinarily sensitive scans of the cosmos, capable of detecting faint artificial signals that might be broadcast by distant civilizations. Parallel efforts include optical SETI programs that monitor millions of stars for brief laser flashes, potential beacons or communication signals, while initiatives like Breakthrough Listen have brought significant funding, technological expertise, and global collaboration to the quest. Despite these efforts and the technological marvels enabling us to scan the universe more thoroughly than ever before, each passing year of continued silence deepens the mystery. The Fermi paradox: why, given the universe's vastness and the high probability of life-supporting planets, we have yet to find any definitive signs of extraterrestrial intelligence, becomes even more perplexing. We are left to ponder three broad possibilities. Perhaps humanity is extraordinarily alone in the cosmos. Perhaps we are among the first civilizations to emerge. Or maybe we are simply blind to the signs of intelligence that are out there, hidden from our detection. What if, however, the silence itself is the most telling answer? Could it be that advanced civilizations have learned, or instinctively understood, that the universe is far more perilous than it appears? Perhaps survival in the cosmic arena requires a secret discipline, the art of invisibility. This leads us to a dark and compelling hypothesis: the Motors dark forest hypothesis. This hypothesis, inspired by Liu Cixin's acclaimed science fiction trilogy, particularly the second volume titled The Dark Forest, envisions the universe as a vast, silent, and deadly place. Humanity's first contact with extraterrestrial intelligence, according to this scenario, might be accompanied by a dire warning: do not answer. The message, transmitted from an alien pacifist attempting to shield Earth from predators lurking in the cosmic shadows, underscores a chilling reality. It suggests that revealing our location or broadcasting our existence could be catastrophic because every civilization, aware of the destructive potential of others, chooses silence out of self-preservation. The core idea of the dark forest hypothesis is that the universe is teeming with intelligent civilizations, but they all remain deliberately silent. Like hunters stealthily moving through a dark and dangerous forest, each civilization is acutely aware that others are out there, possibly watching, waiting, but they dare not reveal their presence. The first rule of cosmic survival in this view is straightforward yet terrifying. Any civilization capable of interstellar travel is also capable of interstellar destruction. This game-theoretic logic is stark. When two civilizations encounter each other across the vast distances of space, each faces a fundamental uncertainty. Can I trust the intentions of the other? Are they peaceful explorers or predators? Because the potential consequences of a misjudgment are catastrophic. An advanced civilization might destroy or enslave others to ensure its own survival. Most choose to remain silent, hiding their true capabilities and intentions. This mutual suspicion and strategic silence create a cosmic Cold War, where the universe is a dark, silent forest, filled with potential threats. Even if an extraterrestrial civilization appears to be peaceful and benign, there exists no reliable way to ensure that this peaceful stance will persist over the vast stretches of time required for genuine interstellar interaction. Technological progress in such civilizations tends to grow at an exponential rate. What is harmless today could very well evolve into a deadly threat tomorrow. A society that poses no danger now might, in just a few centuries or millennia, develop planet-destroying weapons capable of annihilating entire worlds. Furthermore, the challenge of communication across the immense distances between stars adds another layer of complexity. Any message intended to convey peaceful intent must be transmitted over light years of space, but such signals are inherently risky. A signal powerful enough to reach another star system could equally serve as a beacon for potential enemies, revealing the location of the sending civilization. Conversely, any technology capable of propelling spacecraft at a significant fraction of light speed, necessary for interstellar travel, could also be harnessed to send devastating weapons or projectiles. In this context, the most prudent assumption is that any detected extraterrestrial civilization should be regarded as a potential existential threat, warranting preemptive action to neutralize it before it can pose a danger. This mindset leads to what scientists have come to call a cosmic Cold War, a universe in which every civilization capable of interstellar travel maintains a cloak of utmost secrecy. These civilizations would monitor their surroundings vigilantly, scanning for signs of other intelligent life, while carefully concealing their own presence. The principle is straightforward: detection equals death. To survive in such a universe, a civilization must achieve perfect stealth, maintaining absolute operational security over cosmic timescales. The unsettling plausibility of this scenario becomes even clearer when we reflect on Earth's own history of communication. Over the past century, humanity has inadvertently broadcast our presence across the galaxy through radio and television signals, radar transmissions, and other forms of electromagnetic radiation. Our planet, in essence, has become a glowing beacon, a cosmic lighthouse, announcing to any potential listeners that Earth harbors a technological civilization. But is it truly wise to be so conspicuous? The debate surrounding deliberate messaging to extraterrestrial intelligence, or METI, exemplifies the inherent tension within the dark forest hypothesis. Since the 1970s, humans have occasionally sent targeted signals towards nearby star systems, including mathematical sequences, cultural information, and even musical compositions. One notable example is the Arecibo message broadcast in 1974 towards the globular cluster M13, a message that will take roughly 25,000 years to arrive at its destination. Critics of METI argue that by actively transmitting our presence, we are essentially exposing ourselves to unknown risks, sending our cosmic address into a universe filled with potentially hostile civilizations that might not have our best interests at heart. These skeptics contend that such deliberate signals could be intercepted or exploited by malicious entities. Supporters, however, counter that our planet has already been broadcasting signals involuntarily. Our radio leakage, television broadcasts, and radar signals have been traveling through space for decades. Since these emissions are already revealing our technological level, proponents argue that deliberate messaging adds little additional danger. Yet the dark forest scenario suggests that both perspectives might be dangerously naive. In a universe teeming with hidden civilizations, any overt display of technological activity could be tantamount to announcing one's location to predators. The harsh mathematics of interstellar warfare lend grim support to this view. A civilization capable of propelling spacecraft at a significant fraction of light speed would possess the technology to deliver devastating kinetic weapons. For example, a probe traveling at just 10% of the speed of light would impact with the energy equivalent of thousands of nuclear bombs. an impact capable of vaporizing entire planets. At relativistic speeds, even small objects become planetary killers capable of wreaking catastrophic destruction upon contact. Detection technologies, which are rapidly advancing and following exponential trajectories themselves, only reinforce this grim calculus. Our ability to identify and track fast-moving objects in space improves with each passing year, but so does the potential threat. The same technological progress that allows us to detect distant threats also enables civilizations elsewhere to develop weapons that could annihilate us from afar, with little warning. In this universe of uncertainties and exponential risks, the safest assumption remains that any signal, any sign of advanced activity, could indicate a dangerous predator lurking in the cosmic shadows. Therefore, the principle of detection equals death becomes a pragmatic if chilling guiding rule. In such a scenario, survival hinges on achieving and maintaining perfect stealth, concealing our presence, our intentions, and our technological capabilities across cosmic scales. This unsettling hypothesis gains significant credibility when we consider humanity's own historical and current behavior. For more than a century, Earth has been unwittingly broadcasting its existence through a flood of electromagnetic signals. Our radio and television broadcasts, radar systems, and various other emissions have painted a bright picture of technological development, making Earth a conspicuous target in the galaxy. Is it prudent to remain so openly visible? The debate over whether to send a civilization endowed with the technological prowess to construct radio telescopes vastly larger than those we possess today could potentially detect Earth's own broadcast signals from hundreds of light years away. Such advanced societies might employ even more sophisticated means of surveillance, monitoring gravitational waves, detecting neutrino emissions, or sensing exotic signatures that we haven't yet conceived of. According to the dark forest hypothesis, these watchers are invariably one step ahead of us. They are always the hunters, observing from the shadows while remaining concealed. This concept also offers compelling explanations for several enduring enigmas associated with the Fermi paradox. The question of why, given the vastness of the universe and the high probability of extraterrestrial life, we see no definitive signs of galactic engineering, no megastructures, no unmistakable evidence of other civilizations' technological endeavors. One explanation suggests that civilizations capable of monumental galactic constructions, imposing structures that showcase their technological might, rarely survive long enough to reach a galactic scale. The very act of building conspicuous monuments might be a death sentence, as such visibility could attract dangerous attention. Similarly, the absence of detectable industrial waste heat or atmospheric pollution on exoplanets aligns with this perspective. It posits that advanced civilizations either deliberately conceal their signatures or actively eliminate those that fail to do so, engaging in a cosmic game of hide-and-seek where disclosure invites annihilation. Even more unsettling is the possibility that Earth might already be under observation by covert extraterrestrial civilizations, who are patiently watching and waiting to see how humanity evolves. In this scenario, our planet becomes a sort of cosmic test, a challenge to determine whether human civilization can mature into a responsible galactic citizen. Will we learn to operate quietly in the universe, respecting the unspoken rules of cosmic coexistence? Or will we follow the destructive path of expansion and conquest that has doomed many civilizations before us? When viewed through the dark forest lens, recent fascination with interstellar objects like Oumuamua takes on a sinister tone. While mainstream astronomy regards these visitors as natural phenomena, comets or asteroids originating from other star systems, the hypothesis suggests a more ominous possibility. They could be scout probes, sent by civilizations monitoring our development from afar. Particularly intriguing are the unusual characteristics of Oumuamua. such as its non-gravitational acceleration and its cylindrical shape, features consistent with artificial objects designed for reconnaissance or surveillance. Similarly, the expanding catalog of unexplained atmospheric phenomena, including the military's acknowledgement of unidentified aerial objects exhibiting flight characteristics beyond our current technological understanding, may be evidence that we are already under the watchful eyes of civilizations adhering to dark forest protocols. These entities observe us silently, gathering intelligence while deliberately avoiding direct interaction, maintaining plausible deniability. The implications for humanity's behavior are profound and potentially transformative. If the dark forest hypothesis holds true, we are faced with a stark choice. We can either learn the art of cosmic stealth and adopt a policy of concealment, thereby increasing our chances of survival and eventual integration into the galactic community, or continue broadcasting our presence loudly and openly, risking detection and possible destruction by more cautious predatory civilizations. Moreover, the window of opportunity to choose wisely may be narrower than we imagine. Other civilizations might interpret our current level of radio emissions as a sign of recklessness or immaturity, an invitation for predators to target us. Some researchers have proposed that humanity should immediately cease all high-power radio transmissions and adopt a strict planetary radio discipline, reducing our electromagnetic signature to avoid revealing our location. This strategy of deliberate silence, if adopted universally, could serve as a vital form of cosmic self-preservation, helping us remain hidden in the shadows of an unfathomably vast universe. Some voices argue that it is already too late. Over the past 100 years, our relentless emissions of radio waves have expanded an invisible sphere of detectability, encircling hundreds of nearby star systems. This realization is profoundly unsettling, especially when contemplating the dark forest hypothesis. A stark perspective suggesting that the universe is far from an empty stage awaiting the arrival of flourishing civilizations. Instead, it resembles a vast, silent ocean teeming with predators, where even the faintest ripple of disturbance could draw fatal attention. Every new radio telescope we construct, every deep space probe we dispatch, every effort to reach out to extraterrestrial intelligence might inadvertently serve as a death warrant for our entire species. Yet within this bleak outlook lies a paradoxical glimmer of hope. If the dark forest theory holds true, then it implies that the universe is indeed brimming with intelligent life. We are not merely unobserved. Rather, we are deliberately kept in the shadows, hidden, silent, and unremarkable, until we demonstrate our worthiness to join the cosmic community. The silence that envelops the universe might not be evidence of loneliness, but rather a form of cosmic discipline, a lesson learned through the most arduous of trials. In this view, survival in the universe's perilous landscape requires an unspoken rule: invisibility. The question that keeps astronomers awake at night is no longer simply whether other civilizations exist. Instead, it is whether these civilizations have mastered the art of concealment so thoroughly that they are beyond our reach forever. More troubling still is the unsettling possibility that some of these hidden entities might have already discovered us, our signals, our probes, our presence, while we remain oblivious to theirs. Have they already observed us, learned from our emissions, and chosen to remain silent? Or are we alone in a universe that is, in truth, filled with silent, watchful observers? This leads us into a realm of profound speculation, bridging science and conspiracy, what might be called the domain of alien conspiracies and covert visitors. Today, the boundary between authentic scientific inquiry and wild conjecture seems more fragile than ever, especially when discussing the potential existence of hidden extraterrestrial visitors within our solar system. Recent years have ushered in an era of startling astronomical discoveries, official acknowledgments of unexplainable phenomena by governments, and an online environment that amplifies speculation at a breakneck pace, often outstripping the rigorous process of peer review. Take, for example, the case of Oumuamua, the first confirmed interstellar object to visit our solar system. When astronomers first detected this cigar-shaped object in 3IATLAS, it was initially regarded as an intriguing yet straightforward example of natural debris, space junk, or remnants from another star system. Its appearance and trajectory seemed consistent with known phenomena, a rocky fragment drifting through interstellar space. However, as further observations accumulated, Oumuamua exhibited behaviors that defied easy explanation and challenged conventional understanding. Most perplexing was its non-gravitational acceleration. Unlike typical asteroids or comets, which drift through the solar system primarily under the influence of the sun's gravity, this object appeared to be speeding up in ways that could not be accounted for solely by gravitational forces. In the case of natural comets, such acceleration is usually caused by jets of sublimating ice, gases escaping from the comet's surface, producing tiny rocket effects. Yet Oumuamua showed no signs of the gas and dust clouds characteristic of active comets, no visible outgassing or tail. It seemed to be accelerating as a comet would, but without the typical indicators of cometary activity. Faced with this enigma, some researchers ventured into more speculative territory. Harvard astronomer Avi Loeb proposed a provocative hypothesis. Could Oumuamua be an artificial construct, a form of alien technology? Specifically, he suggested it might be a light sail, a thin reflective surface powered and propelled solely by radiation pressure from the sun. His calculations demonstrated that, with the right shape and composition, an object like Oumuamua could indeed exhibit the observed acceleration through purely artificial means. This notion, while controversial, opened a new window into thinking about extraterrestrial artifacts, objects engineered rather than naturally occurring, lurking silently in our celestial neighborhood. The response from the scientific community to the mysterious object known as Oumuamua was characterized by both swiftness and a healthy dose of skepticism. While initial intrigue sparked widespread curiosity, experts quickly proposed alternative explanations rooted in natural phenomena. Some hypothesized that Oumuamua could have been composed of solid hydrogen, sublimating silently and invisibly, or perhaps it was a fragment resulting from a disrupted planetary body with unusual thermal properties. The European Space Agency's official analysis echoed this cautious stance, asserting that the most plausible explanation remained natural outgassing, even if such gas was not detectable through Earth-based telescopic observations. This controversy surrounding Oumuamua exemplifies a broader challenge faced by modern astronomy. How to accurately distinguish between phenomena that genuinely warrant serious scientific scrutiny and those that are sensationalized, often mistaking natural processes for signs of artificial intelligence or extraterrestrial engineering. The key to resolving such mysteries lies in the quality and quantity of evidence gathered, the rigor and objectivity of the analytical methods employed, and an unwavering commitment to accepting simple, mundane explanations, even when more exotic or sensational alternatives appear more captivating. In the wake of Oumuamua's departure from our solar system, the scene was set for further interstellar visitors. 2 years later, the solar system welcomed another such object, Comet Borisov. Unlike its predecessor, Borisov exhibited behaviors entirely consistent with what astronomers expected from a natural comet. It displayed a typical coma and tail, outgassed at predictable rates, and followed a trajectory aligned with well-understood gravitational physics. Borisov's behavior served as a perfect control, reinforcing the idea that interstellar objects can and do behave in ways consistent with known natural laws, thus underlining the importance of cautious interpretation. The arrival of the interstellar object designated as 3IATLAS in the year 2025 reignited these ongoing debates. Much like Oumuamua, this latest visitor became a subject of intense speculation, particularly due to its striking green coloration. Social media platforms were abuzz with claims, some breathlessly suggesting it might be an alien spacecraft or an extraterrestrial probe. However, the scientific reality was far less sensational. That luminous green glow was almost certainly the result of the same process that colors many ordinary comets: diatomic carbon fluorescence. This is a natural phenomenon caused by solar radiation energizing simple molecules within the comet's coma, a process well documented and understood by astronomers. The challenge for both scientists and the general public remains the same: to sustain a healthy skepticism without dismissing the possibility of revolutionary discoveries. While the universe is vast and undeniably strange, capable of producing phenomena that might someday prove artificial, the principle remains that extraordinary claims demand extraordinary evidence. Such evidence must adhere to rigorous scientific standards, including reproducibility, detailed analysis, and confirmation from multiple independent sources. This issue becomes even more pressing in the context of the digital age, where claims of alien visitation and unidentified phenomena can spread rapidly across social media platforms. A single unusual observation can generate a flurry of videos, blog posts, and viral threads, each amplifying speculative interpretations and often neglecting simpler, more mundane explanations. This creates a complex information ecosystem, one where sensationalism can overshadow scientific rigor, leading to widespread misconceptions and unfounded fears. Adding another layer of complexity to these discussions is the recent acknowledgement by military and aerospace agencies of unidentified aerial phenomena, objects displaying flight characteristics that surpass known human technology. Such revelations, though cautious and often classified, fuel both excitement and suspicion, further blurring the line between credible scientific inquiry and sensationalized speculation. As these phenomena are investigated and analyzed, the importance of maintaining rigorous standards of evidence and skepticism remains paramount to avoid misinterpretation and misinformation. While officials in defense agencies have been notably cautious about openly claiming that recent phenomena are of extraterrestrial origin, the fact that military sensors have detected objects exhibiting inexplicable behaviors has ignited widespread speculation about the presence of hidden alien observers on Earth. This cautious silence only fuels the intrigue. If there truly are advanced civilizations observing us from afar, what might their surveillance look like? The dark forest hypothesis offers a compelling framework for understanding this. It posits that in the vast cosmic expanse, highly advanced civilizations would prioritize stealth above all else, operating under a principle of cautious concealment. Their technology would be so sophisticated that their probes and monitoring systems would be effectively undetectable by civilizations like ours, which are still in their infancy of space exploration. These extraterrestrial surveillance devices could be designed to mimic natural space objects, asteroids, comets, or even ordinary space debris, camouflaging their true purpose while secretly gathering valuable intelligence on human technological progress and societal development. Supporting this idea is the physics of interstellar probe design, which suggests that such stealthy observation is technically feasible. An advanced civilization could engineer tiny, highly efficient probes capable of avoiding detection amid the billions of small objects populating our solar system. These devices could be powerful enough to monitor an entire planet's electromagnetic emissions, tracking everything from radio signals to atmospheric phenomena, all without revealing their presence. Many of these probes might remain passive, simply collecting data and passing it along without transmitting signals that could betray their artificial origin. From this perspective, every strange or anomalous astronomical object might be a potential disguise, an alien sensor in disguise. Could some near-Earth asteroids actually be concealed alien artifacts, disguising their true nature? Might certain comets be carrying hidden sensors or surveillance equipment embedded within their icy cores? Are there monitoring stations cleverly hidden among Jupiter's Trojan asteroids, those groups of objects locked in gravitational harmony at the planet's Lagrange points, or camouflaged as typical Kuiper belt objects beyond Neptune? The unsettling reality is that our current astronomical surveys are not specifically designed to detect such concealed devices. We mainly catalog asteroids and comets based on their orbits and basic physical characteristics, rarely examining their detailed structures to identify subtle signs of artificial modification or technology. A sufficiently advanced extraterrestrial probe could easily blend in among the countless small bodies drifting through our solar system. To the naked eye, or even to most of our sensors, they would appear indistinguishable from natural debris, until perhaps they are subjected to close inspection or become active. This situation presents a profound epistemic challenge. Just because we lack evidence of alien probes today doesn't mean they aren't hiding there. The absence of proof is not proof of absence. It's entirely plausible that these hypothetical surveillance devices are simply better at concealment than we are at detection. Every unexplained acceleration or anomalous behavior observed in objects like the mysterious interstellar visitors Oumuamua and Mua could be explained by natural phenomena. But it's also possible that they represent the successful camouflage of much more advanced intelligence. The implications stretch beyond pure scientific curiosity and delve into critical issues of planetary security and human sovereignty. If Earth is indeed under watchful eyes, hidden extraterrestrial intelligence observing our progress, what might they be learning? Are they studying our technological capabilities, our biological traits, or our social structures? Are they simply collecting data for knowledge's sake? Or are they preparing for some future form of contact, intervention, or influence? These questions challenge our understanding of our place in the cosmos and our vulnerability in a universe that might be far more surveilled and less open than we assume. These questions defy simple, straightforward answers because they sit at the delicate boundary between genuine scientific inquiry and the realm of inevitable speculation. The scientific method is remarkably effective when it comes to studying phenomena governed by consistent physical laws, things like planetary motion, stellar evolution, or the behavior of gases under extreme conditions. However, when it comes to detecting signs of intelligence that might be actively working to conceal itself, our tools encounter significant limitations. We are, in essence, engaged in a cosmic game of hide and seek, where the rules are unclear, the number of players is unknown, and we have little idea whether the game is even truly underway. The most responsible scientific approach involves maintaining diligent, continuous observation, systematically collecting data, analyzing anomalies with rigor, and remaining skeptical of extraordinary claims. While every unusual object or signal warrants careful investigation, claims of alien intelligence or technological origins demand proof of an exceptional nature. In science, extraordinary claims require equally extraordinary evidence, and until such evidence emerges, caution and restraint are paramount. The universe itself is undeniably strange, so strange that many phenomena already challenge our understanding without adding the assumption of extraterrestrial involvement. It is important to remember that the absence of confirmed extraterrestrial visitors does not necessarily mean humanity is alone in the cosmos. The galaxy could well be teeming with civilizations that are simply far more adept at hiding than we are at discovering them. In a universe operating under what is known as the dark forest principle, an analogy borrowed from speculative astrophysics. Those civilizations that succeed in avoiding detection are the ones that remain safest. Paradoxically, the most successful civilizations might be the ones we never see at all, lurking in the shadows, silent and unseen. But what if some signals we detect are so unusual, so persistent, so clearly artificial, that natural explanations start to stretch credibility? What if the universe, which normally remains silent, begins to break its silence in ways impossible to ignore? This brings us to the realm of unexplainable phenomena, things that simply don't add up, challenging our understanding of cosmic signals and forcing us to reconsider what might be possible. Among these phenomena, few have generated as much excitement and frustration as fast radio bursts, or FRBs. These brief, millisecond-long flashes of radio energy, first identified in archival data from 2007, continue to intrigue scientists because they seem to originate from seemingly random directions in space, with no clear natural cause. For years, FRBs have stood as some of the most tantalizing cosmic puzzles, brief, intense, and utterly alien in their nature. The story of FRBs began with a single, peculiar burst detected by the Parkes radio telescope in Australia. Lasting only about 5 milliseconds, this burst discharged as much energy as the sun does in an entire day, yet it appeared to come from a galaxy billions of light-years away. Its spectral characteristics suggested it had traveled through vast expanses of ionized gas, confirming its extragalactic origin. But it offered no clues as to what could produce such an incredibly brief yet powerful burst of radio waves. For many years, these signals lingered in scientific limbo, neither comfortably explained by known phenomena nor dismissed as mere interference. The possibilities ranged from natural stellar processes, such as cataclysmic events involving exotic objects, to instrumental artifacts or terrestrial interference that might be mimicking cosmic signals. Some researchers even pondered whether these bursts could be evidence of something entirely artificial. Perhaps the focused radio beams of advanced civilizations using interstellar communication or propulsion technologies. The hypothesis that these bursts might be of artificial origin gained some traction because of their extreme brightness and brevity. Such characteristics are more consistent with engineered signals, designed perhaps for interstellar messaging or navigation, rather than natural phenomena, which tend to produce more predictable or less intense emissions. This alternative explanation has fueled ongoing debate about the true nature of fast radio bursts, highlighting how much we still have to learn about the universe's most mysterious signals. The seemingly random spread of these bursts across the sky hinted at a diversity of origins, suggesting they might stem from numerous different sources rather than a single type of cosmic object. This patchwork pattern puzzled scientists, as it pointed to a complex underlying mechanism rather than a uniform phenomenon. What made the situation even more intriguing was the fact that some of these bursts appeared to recur, repeating themselves periodically. Such behavior was difficult to reconcile with catastrophic stellar events, like supernovae or starquakes, that are typically one-off, explosive occurrences. Instead, the repeating nature of some signals hinted at a different kind of process, one that could be activated repeatedly, perhaps implying an artificial origin or a highly energetic yet sustained natural mechanism. Then, in the year 2020, a breakthrough in understanding finally arrived, marking a turning point in the study of fast radio bursts. For the first time, astronomers detected a burst emanating from within our own galaxy, specifically from a well-known magnetar called SGR 1935+2154, located approximately 30,000 light-years away from Earth. This single observation was revolutionary because it provided clear evidence that at least some fast radio bursts are of natural origin. Magnetars are extraordinary neutron stars, remnants of massive stars that have undergone supernova explosions, characterized by magnetic fields trillions of times stronger than Earth's magnetic field. These objects are so extreme that they push the very limits of what matter can endure, and their violent activity can release enormous amounts of energy. When magnetars undergo starquakes, fractures in their incredibly dense crusts, they can unleash energy in mere milliseconds that surpasses the total energy our sun emits over years. The intense magnetic fields of these stellar remnants act as cosmic channels, directing this released energy into narrow beams that sweep across space like powerful lighthouse beacons. The detection of a fast radio burst from SGR 1935-2154 thus served not only as a scientific confirmation that some of these bursts originate naturally from known stellar phenomena, but also as a sobering reminder of the universe's capacity for violence and destruction. The burst's energy was so immense that it temporarily disturbed Earth's ionosphere despite having traveled 30,000 light-years across space. The implications are profound. If a similar burst had occurred much closer to Earth, within just a few hundred light-years, it could have caused significant damage to our technological infrastructure, disrupting satellite communications, power grids, and even threatening biological life through intense radiation effects. While the magnetar explanation provides a compelling natural cause for many fast radio bursts, it does not account for all observed phenomena. The diversity among bursts remains striking. Some repeat regularly, others are one-time events. Some exhibit intricate frequency patterns, while others are comparatively simple. Additionally, these bursts originate from a variety of environments, some from active star-forming regions bustling with stellar nurseries and others from seemingly empty, quiet regions of space, further hinting at multiple different physical processes behind their origins. The story of cosmic flashes becomes even more tangled when we consider other persistent anomalies in the universe that continue to defy easy explanation. For instance, the famous WOW signal detected by the Big Ear radio telescope in 1977 remains one of astronomy's most enduring mysteries. Lasting for about 72 seconds, this signal exhibited characteristics that closely resembled an artificial origin, sparking speculation about extraterrestrial intelligence. Despite the excitement it generated, the signal was never observed again, despite numerous follow-up efforts spanning decades. Recent hypotheses have attempted to explain it as a natural phenomenon, possibly a reflection of terrestrial radio emissions bouncing off a dense cloud of hydrogen atoms, or perhaps a transient emission from a comet with an unusually dense hydrogen envelope. However, these explanations remain purely speculative, and the precise nature of the WOW signal's origin continues to puzzle researchers more than 4 decades after its initial detection. This persistent ambiguity underscores how much remains unknown about the cosmos, how many phenomena are truly natural and how many might be signals or signs of something more extraordinary. The universe's silence, punctuated by such enigmatic signals, invites a profound reflection on the limits of our understanding and the vastness of the unknown. Similarly, the star known as Chicxulub 462-852, more famously called Tabby's star, ignited a whirlwind of intrigue within the astronomical community when citizen scientists first uncovered its peculiar pattern of brightness fluctuations. Unlike most stars, which exhibit relatively predictable luminosity changes, Tabby's star would sporadically dim by as much as 22%, a level of variation far exceeding what conventional stellar physics or planetary transits could readily explain. This unusual behavior sparked a flurry of initial speculation, with some proposing that the star might be encircled by enormous alien megastructures, perhaps sprawling solar collectors or vast habitat rings engineered by an advanced civilization, harnessing energy or creating artificial shading. However, subsequent detailed observations have largely challenged and diminished the credibility of these extraterrestrial megastructure hypotheses. Instead, the evidence points toward wavelength-dependent dimming, a characteristic more consistent with clouds of dust or debris rather than solid constructed objects. The most plausible explanation currently favored involves irregular clouds composed of comet fragments or asteroid debris intermittently passing in front of the star, temporarily obscuring its light in a manner that varies with wavelength. Despite this, the precise mechanism behind these fluctuations remains elusive, and Tabby's star continues to defy a full understanding of stellar behavior, exhibiting variations that push the limits of astrophysical models. This case exemplifies both the allure and the danger inherent in anomaly-driven astronomy. Unusual observations can serve as the harbingers of groundbreaking new physics or reveal previously unknown astrophysical processes. The discovery of pulsars in 1967, for instance, initially ignited speculation about signals from intelligent extraterrestrial sources, sometimes whimsically called little green men, before scientists recognized that these signals originated from neutron stars, objects so dense and extreme that they had once been considered theoretically impossible. Similarly, gamma-ray bursts, which puzzled astronomers for decades, are now understood to be the universe's most energetic explosion since the Big Bang, revealing violent phenomena that shaped the cosmos. Yet the challenge lies in discerning true revolutionary phenomena from more mundane processes masquerading as cosmic enigmas. Our pattern-seeking brains are remarkably skilled at finding signals amidst noise, a trait that has served humanity well in many contexts. However, this same capability can lead us astray, causing us to interpret natural processes as artificial intelligence or alien technology, when in reality they are simply the universe's complexity at play. The key, as the eminent scientist Carl Sagan emphasized, is to tread carefully along what he called the fine line between skepticism and wonder, remaining receptive to extraordinary possibilities while demanding extraordinary evidence before accepting them as fact. Modern astronomical surveys such as the Zwicky Transient Facility and the forthcoming Vera Rubin Observatory are poised to revolutionize our capacity to detect and analyze cosmic anomalies. These facilities will monitor millions of stars simultaneously, increasing the likelihood of catching rare transient events that earlier surveys might have missed entirely. Advanced computer algorithms will play a crucial role, automatically flagging unusual behaviors for immediate follow-up, enabling astronomers to respond rapidly and gather more detailed data. Nonetheless, this flood of high-quality data introduces new challenges. As detection sensitivity improves, so does the number of phenomena, most natural, some potentially artificial, that we observe. Distinguishing between the two will not only require more sophisticated instruments but also the development of refined theoretical frameworks. Models that can help us interpret what signatures might genuinely indicate the presence of an advanced civilization. The ongoing search for unmistakable techno-signatures, clear, unambiguous evidence of extraterrestrial technology, is evolving well beyond the realm of simple radio signals. Scientists are increasingly exploring alternative avenues, analyzing the atmospheres of distant exoplanets for industrial pollutants, searching for artificial structures that might partially obscure stars, like Dyson spheres, or hunting for laser pulses that could serve as interstellar beacons. Each of these approaches broadens our toolkit and deepens our potential to recognize signs of intelligent life. Yet amid this promising progress, we must remain cautious, balancing curiosity with rigorous scientific scrutiny to avoid mistaking natural phenomena for signs of alien technology. An endeavor that requires patience, skepticism, and a willingness to accept that some mysteries may remain forever elusive. Astronomers now employ a diverse array of advanced survey techniques in their relentless quest to uncover signs of extraterrestrial engineering or clandestine cosmic activity. One such method involves meticulously searching for an unusual excess of infrared radiation, a potential signature of Dyson spheres, hypothetical megastructures that advanced civilizations might build to harness stellar energy. These colossal constructs, if they exist, would absorb a star's light and re-emit it as waste heat, producing a distinctive infrared glow that our instruments could detect from afar. In addition to infrared observations, scientists are actively seeking out laser pulses embedded within optical data streams, brief, high-energy flashes that could signify deliberate interstellar communication efforts. These laser signals, if detected, would stand out sharply against the cosmic background, acting as unmistakable beacons of intelligence. Complementing these searches are investigations into anomalous transit patterns in starlight, unusual dimming or brightening events caused by vast structures passing in front of stars. These patterns could betray the presence of sprawling megastructures, such as Dyson spheres or other engineered constructs designed to manipulate stellar radiation or planetary environments. Every new technique brings with it a dual-edged potential: the exhilarating possibility of groundbreaking discovery and the sobering risk of false alarms or dead ends. Perhaps most compelling of all, these ongoing explorations serve as a stark reminder that the universe continues to harbor profound mysteries, enigmas that defy straightforward classification or understanding. Whether these anomalies are ultimately explained as natural phenomena, such as peculiar stellar activity, interstellar dust, or rare cosmic events, or as evidence of something far more exotic, they challenge the very limits of our scientific comprehension. In a universe capable of producing the most enigmatic entities known, neutron stars, black holes, and the mysterious dark energy, perhaps it should come as no surprise that certain phenomena persist in confounding our current models. The uncomfortable reality remains that our grasp of cosmic processes is fragmentary at best. We comprehend only a tiny fraction of the vast, intricate tapestry unfolding around us. Each time we unravel a mystery, it often reveals new layers of complexity, prompting fresh questions that deepen the enigma. Every anomaly we manage to explain tends to point toward even more profound puzzles lurking just beyond our current understanding. Occasionally, in the depths of our datasets, something appears that resists all categorization, an anomaly that defies explanation within the known laws of physics and natural phenomena. What if one day the noise in the cosmic background, so far dismissed as random or mundane, resolves into a pattern that we simply cannot dismiss as natural? What if the next unexpected signal we detect isn't just unusual but unmistakably artificial, bearing the hallmarks of intelligent origin? As we approach the culmination of our exploration into the universe's most perplexing mysteries, what some might call the catalogue of cosmic dread, a paradox emerges that is arguably more unsettling than any individual threat. The universe appears to be both perilously dangerous and eerily silent. This silence isn't merely the absence of sound, it is the conspicuous lack of detectable signs of other intelligent civilizations. This profound quiet might well be the most terrifying discovery of all, for it suggests that despite the universe's vastness and its capacity for producing violent phenomena, ranging from the icy peaks of the Oort Cloud to the crushing depths of black hole event horizons, from gamma-ray bursts unleashed by dying stars to hypothetical cosmic waves capable of rewriting the fabric of reality itself, the cosmos remains silent about the presence of other intelligences. Each of these cosmic threats operates on scales that dwarf human experience, wielding energies so immense that a single event could obliterate our civilization in mere milliseconds. Yet remarkably, these phenomena obey the fundamental laws of physics, laws that allow us to model, predict, and in some instances defend ourselves against them. We have progressed from helpless victims, powerless before asteroid impacts or stellar explosions, to active participants in our own cosmic security. Modern surveys, such as the ATLAS and the Zwicky Transient Facility, scan the skies nightly with ever-increasing precision, cataloging potentially hazardous objects and tracking their trajectories with extraordinary accuracy. Despite these technological advances, the universe's silence persists as a stark and daunting enigma. It hints at a deeper, perhaps more sinister truth, that intelligence itself might be inherently rare, fragile, or even self-destructive. This silence could be a reflection of a cosmic landscape where civilizations learn that visibility invites danger, where the very act of revealing oneself is a gamble with existential stakes. The universe's apparent quietude, then, might be a form of cosmic prudence, a collective lesson learned by every intelligent species that has risen to technological maturity. Our own trajectory offers a glimpse of hope amid this cosmic darkness. From the catastrophic impact that ended the reign of the dinosaurs 66 million years ago to NASA's successful deployment of the DART mission in 2022, humanity has evolved from a passive recipient of cosmic chaos into an active guardian of its own future. Our nightly sky surveys, powered by instruments like the ATLAS and the imminent advent of the Vera Rubin Observatory promises to fundamentally transform our capacity to identify long-period comets and other cosmic threats well in advance, years or even decades before they could pose any real danger to our planet. This technological leap forward signifies a monumental stride in the ongoing effort to safeguard Earth from celestial hazards. However, despite our rapidly improving proficiency in planetary defense, a stark and unsettling reality persists. Our limitations remain profound and in some cases fundamentally unbridgeable. While we can effectively maneuver small asteroids, nudging them slightly off their collision courses with Earth through various deflection techniques, we find ourselves virtually powerless against the colossal interstellar giants that have long haunted our most vivid cosmic imaginings. Think of the hypothetical monsters, comets of unimaginable size like Thanatos or Leviathan, massive enough to dwarf anything we've encountered or even conceived. Then there are rogue black holes, drifting silently through the dark voids between stars, their gravitational influence capable of devastating entire planetary systems if they happen to pass too close. Add to this the terrifying potential of gamma-ray bursts, sudden and intense flashes of high-energy radiation that could blanket our biosphere in lethal radiation without any prior warning, wiping out complex life in a matter of moments. Against such formidable forces, the efficacy of early detection shifts from a primary means of prevention to a more sobering reality. It becomes a matter of acceptance. In other words, early warning might still save lives, but it cannot guarantee immunity. And often it is more about knowing what is coming than being able to stop it. This stark truth underscores a fundamental asymmetry: what we are capable of detecting and countering versus what we are vulnerable to. An imbalance that fuels deep-seated fears among astronomers and planetary defense specialists alike. What truly keeps these experts awake at night isn't just the catalog of known threats, asteroid impacts, solar storms, or other quantifiable dangers, but rather the vast ocean of the unknown. It is the objects lurking within our blind spots, the phenomena we have yet to learn how to detect, and the dangers rooted in physics that remain beyond our current understanding. The universe, in its infinite complexity, conceals threats that operate according to laws and principles we have not yet deciphered, and this uncertainty breeds a profound and persistent existential dread. This ominous ambiguity extends far beyond the realm of physical risks. It strikes at the very core of our understanding of humanity's place within the cosmic tapestry. Are we truly alone in a universe that rarely produces intelligent life and only sustains it fleetingly? Or are we early explorers in a cosmos teeming with consciousness, with civilizations that have long since risen and fallen? Alternatively, might we be surrounded by silent civilizations, galactic neighbors that have mastered the discipline of perfect concealment, deliberately hiding their presence to avoid detection or conflict? Each of these scenarios carries weighty implications for how humanity should comport itself as a species. If we are truly alone, then our consciousness is a rare and precious gem, a luminous, fragile bloom in an otherwise unconscious universe deserving of our utmost protection and reverence regardless of the cost. If we are early in the cosmic timeline, we shoulder the immense responsibility of pioneering interstellar engineering and navigating the challenges that come with it, an unprecedented role as cosmic trailblazers. Yet if we are ensconced within a silent, dark forest of civilizations practicing the cosmic equivalent of stealth, then our current behaviors, our radio transmissions, our interstellar probes, our efforts at communication may be perilously naive. In this dark forest paradigm, our very attempts to announce our presence could serve as a beacon, drawing the attention of civilizations that have learned to remain hidden out of fear. Our signals, be they radio broadcasts or intentional messages, might inadvertently mark us as naive or reckless, painting a target for those who understand that silence is survival. The very act of emitting signals, of trying to reach out, could be akin to leaving a cosmic calling card, alerting others to our existence and consequently to our vulnerability. This silence paradoxically becomes a phenomenon worth studying in its own right. Why do we see no unmistakable signs of galactic engineering, no sprawling Dyson spheres capturing starlight, no megastructures detectable through their waste heat? Why do even the most sensitive radio telescopes fail to pick up signs of interstellar commerce, communications, or the faint leakage of alien entertainment systems? Perhaps the unsettling answer is not that intelligence is absent, but that it is so abundant and cautious that civilizations have learned the art of invisibility. In such a universe, the absence of detectable signals might be the most telling clue that many, if not most, advanced civilizations have adopted a policy of deliberate concealment, choosing silence over exposure to reduce their risk of annihilation. In essence, the silence itself could be the most profound evidence of a universe saturated with life, each civilization operating under a strict code of cosmic discretion, avoiding behaviors that might reveal their positions or intentions. The implication is startling, that many civilizations have imagined a universe where countless civilizations have mastered the art of remaining unseen, cloaked in such profound silence that the cosmos appears utterly empty to our instruments. Yet beneath this apparent stillness, the universe could be alive with covert activity. Hidden signals, subtle disturbances, and clandestine exchanges that our current technology cannot detect. In this scenario, the most successful and advanced civilizations might be the ones we will never directly observe, simply because they have learned how to hide their presence with such finesse that only those who have achieved similar mastery could recognize their existence. It is only once we demonstrate comparable levels of cosmic stealth, by mastering the art of silence ourselves, that we might earn our place in the cosmic community and finally establish contact. This perspective fundamentally reshapes our entire approach to human space exploration. It elevates our scientific pursuits into a profound existential challenge, a test of our maturity not just as explorers but as intelligent beings capable of understanding our place in the universe. Are our deep space probes being watched by unseen observers monitoring our every move? Do our radio signals unintentionally broadcast into the void, reveal us as primitive beings still unready for interstellar companionship? Could it be that our entire civilization is being subtly evaluated, judged by standards and criteria beyond our understanding, criteria that determine whether we are deemed worthy of joining the cosmic society or forever relegated to silent isolation? The psychological burden of contemplating such possibilities can be overwhelming. It's one thing to worry about asteroid impacts or gamma-ray bursts, threats governed by the known laws of physics which we can study, model, and prepare for. But it's an entirely different matter to suspect that every decision we make as a species, every technological advancement, every broadcast, every step into space, might be observed, judged, and perhaps even evaluated by intelligence far more advanced than ours. The implications of this uncertainty are staggering, and the weight of such a cosmic scrutiny can be difficult to bear. Yet within this uncertainty lies a strange and paradoxical form of liberation. If the universe's silence is a deliberate choice by its inhabitants, an intentional act of concealment, then that silence itself becomes proof that intelligence can survive and flourish on cosmic timescales. The very fact that we see no evidence of widespread galactic civilizations is not necessarily a sign of failure. Instead, it could be the hallmark of success, an indication that advanced beings have learned the wisdom of restraint, choosing silence over noise, invisibility over exposure. In this light, the absence of obvious civilizations becomes evidence not of a universe barren of life, but of a universe populated by wise, mature entities that understand the importance of discretion. From this perspective, humanity's current state resembles adolescence in a cosmic sense. We are at an age where we have developed the technology to create dangerous weapons and explore distant worlds, yet we still lack the wisdom to wield these tools responsibly. We are sophisticated enough to detect some cosmic threats, but naive enough to broadcast our presence indiscriminately, revealing ourselves to the universe at large. We are inquisitive and curious, capable of asking profound questions about our origins and our role in the cosmos. But we are not yet wise enough to fully grasp the consequences of our inquiries or the potential dangers of revealing ourselves to unseen observers. Moving forward, our journey requires a delicate balance, an equilibrium between cautious vigilance and open curiosity. We must continue to scan the skies diligently for signs of danger, developing ever more refined tools to distinguish natural phenomena from potential artificial signals. At the same time, we must remain aware that some threats or messages may be intentionally evading detection, designed to remain hidden from our view while possibly observing us with equal care. Developing better methods to tell natural from artificial, to identify genuine signs of intelligence, and to recognize deliberate mimicry is crucial. Most importantly, we must cultivate what might be called cosmic humility, an acknowledgement that we are newcomers in a universe that operates according to its own ancient and inscrutable logic. The rules of what constitutes a civilization's presence or absence were written long before Earth was even a speck in the cosmic clock. Our survival may depend not on rewriting these rules, but on learning to follow them, on understanding that silence and invisibility are often signs of strength, not weakness. In essence, we are at a pivotal point. Our exploration of the cosmos is not only about discovery, but also about understanding our own readiness and responsibility within this vast, silent universe. The path to genuine cosmic maturity involves mastering the art of silence ourselves, learning when to speak and when to remain quiet, when to reveal ourselves and when to hide. Only then can we hope to find a place among the stars, not as reckless explorers broadcasting our presence indiscriminately, but as wise, stealthy participants in a cosmic community that values discretion above all. The entire catalog of cosmic dangers we have delved into, ranging from the catastrophic impacts of comets to encounters with elusive black holes, from the destructive energy of gamma-ray bursts to the enigmatic waves that could ripple through the fabric of space-time, serves as more than a mere inventory of existential threats. It stands as a profound reflection on humanity's fragile and uncertain position within a universe that operates on vast scales and time frames far beyond our daily comprehension. As biological beings evolve to thrive on a single planet, our minds grapple with phenomena that stretch across entire galaxies and epochs, challenging our understanding of reality itself. Yet despite these staggering distances and durations, we continue our relentless quest as cosmic detectives, driven by a vital instinct: to know. For in refusing to remain blind to our celestial surroundings, we recognize that ignorance of what lurks in the darkness could be far more perilous than the knowledge we seek to uncover. Every danger we identify, every model we refine, every technological safeguard we devise, no matter how small, serves to chip away at the vast unknown, inching us closer to survival in an uncertain universe. Each step forward in understanding enhances our odds, however marginally, of enduring through the cosmic storm. The silence that envelops the universe around us, whether it signifies profound loneliness or cosmic discipline, remains one of the greatest mysteries. It may suggest that intelligent life is exceedingly rare, beyond the limits of our imagination. Or it might indicate that such civilizations are abundant, yet masterfully hidden, employing silence as their shield. Perhaps we are the first to pose these questions, or perhaps we are the last, risking catastrophe with every answer we seek. What truly terrifies scientists is not solely what we have discovered about the threats lurking in the cosmos. It is the unsettling suspicion that the greatest danger lies in what remains unknown, those unseen entities and unseen forces that could strike without warning, in a universe capable of concealing entire civilizations behind perfect veils of stealth, harboring rogue black holes in the dark interstices between stars, and unleashing gamma-ray bursts across galactic expanses with no prior indication. Our most profound fear is not the monsters we can see approaching, but those that have learned to come silently, invisibly, and undetectably. The ultimate question shaping humanity's destiny is no longer merely whether we are alone among the stars. Instead, it is whether we possess the wisdom, foresight, and humility to survive whatever truths the universe might reveal, whatever form those truths take. For in the end, our future hinges not just on our technological capabilities, but on our capacity to understand our place amidst the staggering, silent vastness of space, and to navigate its hidden perils with prudence and awareness. The answer, whatever it may be, could determine whether we endure as a species or fade into the cosmic shadows, unprepared and unnoticed.